Okay, so we are now going to start induction. This is the audience participation portion of this talk. So that's only half in jest. Great, thanks Ryan. Quite a few of you in this classroom I have taught or am teaching induction, maybe even more than once. And so I will potentially, not call on people, but I'm gonna need help because I'm a bit at my wit's end now. And I've only done 3 hours. I mean, poor Van's already done the 6, but. Okay, so let's jump to the first slide here. I'll go like this. And this will be familiar to a bunch of you, I know, but we'll go through this one again. So I'm interested in discovering what is the sum of the first n odd natural numbers. So what's 1 plus 3 plus 5 plus 7 up to n? Well, not up to n, up to something else, depending on n. We'll write it out in a moment here. Okay? And I want to do this example to motivate the method of induction. So we'll do this, then we'll learn induction, and then we'll prove a bunch of stuff with induction. We will speed run induction here, maybe. We'll get a lot done, I think. Okay, so let's start off with a couple examples here. Let's just list different sums of consecutive odd numbers here and speculate on a conjecture we want to make here, okay? So the sum of the first odd integers is just the number 1 by itself, right? That's it. There's not much to say beyond that. The sum of the first 2 odd integers is 1 plus 3, and then 1 plus 3 plus 5. Let's just write a couple more down. 1 plus 3 plus 5 plus 7. And, okay, one more. 1 plus 3 plus 5 plus 7 plus 9. Everything okay? Yeah, okay. Questions are always welcome, of course, you guys. So, all right. So let's write on the left here what these sums are, just by simple computation. What's up, Ryan? Oh, the full screen. Yeah, okay, yeah. I give my students such a hard time for not doing it, but okay. All right, so this one is 1. What's the sum of this next one? Real brain buster. Exactly. 4. And then? 9. 9. Thomas, I hear you. 16. 16. And 25, exactly. And what do you think is going to be the next one then, without even writing it out? 36. Yeah, gotta be 36, right? Excellent, okay. And there's a few things going on here. One, they're not that hard to just sit down and add here, even at 10 p.m. But there's a shortcut here that's very, very helpful, before we even observe the pattern. When you answered to me 25 here, how many of you actually added up all of these numbers? Some did. Wrong answer, right? No. Keith, did you really? I don't believe you. Yeah, okay. So what was observed, I hope, by everyone was that if I wanted to add 1 plus 3 plus 5 plus 7 plus 9, but I already knew 1, 3, 5, 7 gave me 16, I simply needed to increment by 9. So to 16, I could add 9 and get the next one, and so on. So to get 36, I just added whatever I had for the previous plus 11. And we can continue that process here. We can predict what the next one will be. Well, there's 2 things going on here. We can predict either by saying, oh, 36 plus 13 is going to be 49. But there's also something else pretty obvious going on here as well. Right? What's in this left column here? Yeah, well, the whole full left column. What's the description of those numbers? What types of numbers are there? Yeah, they're perfect squares, right? This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared, right? That can't just be a coincidence. Surely there's something going on, and we want to prove what's going on. But in order to prove something, we need to make first a conjecture. We need to say, what do we think this is in general? So I'm going to write this as a conjecture to start with. All right? And the idea is, okay, I want a formula in terms of n. Right? That's what the problem asked us, is what is the sum of the first n odd integers? So let's try to articulate what that is and what the formula should be, based on our experience here. So how would I write down the first n integers, right? 1 plus 3 plus 5 plus 7 plus, what's the nth one look like? It's not n itself, right, because n might be even or odd. Anyone see what it is? What's the general form of an odd integer? 2n plus 1, right? And so this is either going to be 2n plus 1 or maybe 2n minus 1, depending. We have to be, we'll double check ourselves here. I think it's 2n plus 1. But maybe it's not.
No, it's 2n minus.
It's minus? Okay, sounds like minus, yeah, for this one. We get minus there, right? And we can check this. I like to maybe do it by example here, right? So when n equals 5, when I'm adding up the first 5 here, right? 2 times 5 is 10 minus 1 is 9. It matches up with that guy there, okay? Also, when n is 1, I get 2n, so 2 minus 1, I get 1. Right? Okay, so this is the correct, this is n odd integers. And this should be equal to something. Well, obviously some power of 2. Let's figure out the correct power of 2. Candidates might be n minus 1 squared, n plus 1 squared. Right? Those are all reasonable things, but we can easily figure it out, right? This 6 here corresponds to what over here? Yeah, it's literally the number of terms over here. So, okay, well that means this is just n, right? Just n squared. So that's the formula. And you can double check against those, but this matches up, okay? Okay, have we proved this formula? No, not at all, right? We conjectured this. We've proved that it holds for n equals 1 up to 7, but that's hardly a proof, right? And we could keep continuing to confirm it. In fact, you could use a computer and confirm it up to, billions and billions. That still, of course, wouldn't be a proof. Maybe the number right after the one that the computer can do, it fails, right? Unlikely, but we don't know for sure. There are instances where we have these patterns that go on for a long time and fail at absurdly large numbers, okay? So I actually want to prove this thing here, all right? In order to prove this, I'm going to need something called induction, which I will introduce to you on the next slide in a moment here. But before I do that, I want to see why, some kind of recursive argument would be helpful for us here, right? And we already kind of got a taste of why that might be helpful, right? Answering the 6 question, it was helpful to know the 5 question, right? Knowing the 5 question, I could be like, oh, I can just plug it in here, add 11, and then get the 6th answer. Once I know the 6th answer, I can just plug it in here, add 13, and get the 7 answer, right? And I want to see if that can help me in general. And let's speculate what this might look like. Suppose I told you what the sum of the first n minus 1 odd integers were, right? The previous, right? I'd like to discover the 7th formula, say I already know the 6th. Let's imagine this abstractly. So imagine I knew 1, 3, 5, 7. What would be the n minus first odd integer in this format? N minus first. These are the first n odds. What would be the one prior to 2n minus 1? 2n minus 3, exactly. 2n minus 3, or if I really like, it's 2 times n minus 1 minus 1 at the same time, right? That's like, this value here tells you how far you are. Now suppose I told you that this equaled n minus 1 squared. Okay? We don't know that. In fact, if you look at what's on the board here, that's really no different from what we want to prove. It's just a different variable name, n minus 1 instead of n. Right? But just for a moment, suppose you knew this. So suppose we knew this guy here. Could we use that to try and prove the general formula? Well, we saw a moment ago that if I look here, I can plug this answer in for most of this to get an answer here, right? So let's actually try that. I want to show that this holds, given this thing here. Well, what can we do? Let's write down the left-hand side of this, right? So 1 plus 3 plus 5 plus up to 2n minus 3 plus 2n minus 1, right? I, in this occasion, express the previous to last term as well, just so it's easier to see. This line here is just what's written here. I want to show that it's the same as n squared. I can't write down equal to n squared yet because I don't know that, but what do I know? What is this equal to? N minus 1 squared. And why? Because I said so, because I said we're allowed to use that. Ordinarily you can't, right? So n minus 1 squared, this is by magic. Don't forget plus 2n minus 1, right? This extra term I didn't account for. This I could capture up into this, but this is left over. That's the same over here as when I substitute 1 through 9 for 1 through 9 here. I mean substitute 25, and for 1 through 9 I have this 11 left over. What can I do with this thing here? Yeah, just FOIL it out, see if simplifies or something nice happens. So we get n squared minus 2n plus 1 plus 2n minus 1. Right? This was the leftover stuff. That's what happened with FOILs out. And look, something beautiful happens. This and this and this and this cancels, and I'm just left with n squared. Okay? Which is what I was hoping to prove. I was hoping to prove that this sum equaled n squared. Okay? But I kind of cheated, at least for the moment. I used, some forbidden knowledge. I used this thing here that, we think is true, but isn't proving that this is true equivalent to proving that this is true? And so aren't we using the thing itself to prove the thing we want? At the moment, yes, but with a few slight tweaks, this method will be perfectly permissible. Notice, what I did not do was say, because this is true, plug in n for n minus 1, and that proves the formula there. I'm not plugging into this formula, I'm using it as a tool, a substitution tool. Okay, there's an important difference. Okay. So, let me jump to the next slide here. And I forgot how to do this. And this is the theorem of induction. This will be our tool that allows us to solve this problem here. Okay? So what does induction say? What is the theorem of induction? And I'll explain why this is true, and I'll even give you guys like a metaphorical reason that I know a lot of you guys have seen, but it is still helpful. So suppose I have these mathematical statements, S1, S2, S3, S4, up to S, well, there's no S infinity, but they go on forever. Okay? For instance, this could be an S1, right? The claim that 1 plus nothing equals 1. That's not a very interesting claim, but it is a claim. Then here's S2, that 1 plus 3 is 4. Here's S3, S4, S7, and in general, this is our S7 here. Or S7, Sn, right? There's that. And this over here actually is an Sn minus 1, right? All of these things are different mathematical statements that I could claim to be true, and I would like to prove that they all work. That 1, 2, 3, 4, all the way up to forever, all work. And what the principle of induction says is I can do that if I can satisfy these two bullet points here. As long as I can do these two bullet points individually, S holds on all input values, okay? Now what are these two things? First, I need to check that S1 is true, okay? In this specific example, is it easy to check that S1 is true? Like almost too easy. S1 was the statement that 1 equals 1. It doesn't get any easier than that. Or, well, it could get that could be the hardest thing in the world too, maybe, but we're not going in that direction. And then the second one is, notice what this says here. This says for every k, that's not really the important part here, this says that if sk is true, then sk plus 1 is true. Now, that's a little different from what I wrote over here, but what this is saying is that if I assume that the statement for sk is true, whatever it may be, over here, sk would look like 1 plus 3 plus 5 all the way up to 2k minus 1 equals k squared. That would be sk. If I assume sk is true, can I prove that sk plus 1 is true? The next statement, right? So using the previous, can I prove the next? That would be my goal. Here I've changed variables. In this instance, I went from Sn minus 1 to Sn. In this slide here, I went from Sk to Sk minus 1, okay? Sorry, from Sk to Sk plus 1. Typically, you don't want to go backwards, although near the end, I will show you one instance where you can get away with going backwards. It's extremely cool if I'm still standing at that point, so. All right. Okay, so I want to explain why this method works, what's going on, why this isn't cheating. And actually, in this, I'll essentially prove it to you as well. So let me just use the ladder metaphor, because drawing dominoes is harder. So let's imagine we have this ladder, right? And this ladder goes off into infinity, and each rung on the ladder are these statements. They're sort of hierarchical. There's S1 is on this rung, S2 is on this rung, S3 is on this rung, Sn, say is somewhere here, and it just goes on forever, okay? And I'm interested in proving that every one of these rungs, their corresponding statement is true, right? All of them are true. How would I go about doing that? Well, induction says, here's what you need to do. Induction says, in order for these all to be true, you need to convince me of two things. First, is S1 true or not? Okay, this whole process does not start unless S1 is true, okay? The second thing is says, hey, for some random k, if I assume Sk is true, is the next one follow from it, right? Whether or not Sk is true, I don't actually know, but if I assume it's true, does Sk plus 1 follow from that? So that's asking, say just arbitrarily, here's Sk, does Sk plus 1, can I argue it given Sk, right? Assuming this point here, can I get to this one? So I'm allowed to use this information and maybe whatever else I have at my disposal, okay? Now in the ladder, what does this mean? Let's suppose that our statements Si are just the simple statement that I can reach this rung on the ladder, okay? So Sn is the statement, I can reach rung n on the ladder. So S1 is that I can reach the first rung. S2 is that I can reach the second rung. S1 million is that I can reach the 1 millionth rung. And I'm interested in convincing you I can reach anywhere on that ladder without actually demonstrating it explicitly. Like, I want to convince you I can get to the millionth thing. You're not going to sit and wait for me to climb to it. I want to give you a general argument that I can always get there. And induction says, in order to convince you, I need to convince you of two things. First, that I can even reach the ladder. Okay? If the ladder starts too high on the ceiling, like no matter how well I can climb it, if I can't get to it, I can't start. But in some sense, the more important thing is I need to convince you that no matter where I'm on here, I can always get to this next rung on the ladder. Now, a typical ladder, rungs are evenly spaced, and like if I demonstrated, hey, I can go from 7 to 8, you'll be like, oh, okay, you could go from 1 million to 1,000,001. Like there's no difference between those things. And that's what induction says, that hey, if I can start the ladder and convince you in general I can go from here to here, then putting those two things together, I can reach anywhere I want without actually demonstrating it, right? How? Well, let's put the two together. Suppose I want to convince you literally I can get to the millionth, right? And I've convinced you of two things, not directly that I can get to the millionth, but I've convinced you, A, I can reach the ladder, and B, that anywhere I'm at, I can get to the next rung. Do you believe I can get to the millionth now? Let's put those two things together. Can I get to S2 with this information? Yeah, I can get to S1, and this says, oh, I can go from 1 to 2. Great, I'm at 2. Now the rule says, oh, I can go from 2 to 3, so I can get to 3, 3 to 4, and so on. I don't actually have to do it, I've just told you the general strategy. Yeah, Thomas?
Are you supposed to be like big right now on the screen?
How can you tell? Yeah, yeah, big would be better here. Yeah, as usual. Thank you very much. So, yes. Yeah, okay, so now our ladder's a little more easy to see in this case, okay? That's my metaphor. I've only convinced you maybe that this should prove that I can climb any ladder, but it goes the same for any mathematical statement, right? If you have a statement like this here, and I can convince you that it holds when s is 1, and I can also convince you that whenever it's true for sk, it's also true for sk plus 1, then it works for all of them with this n input. Typically we write it like this, saying that it works for all infinity many of them. I mean, that's the same as just saying it works for all n, okay? This variable is going from sk to k plus 1. That was the model here, but I could have also argued instead that, oh, I can in general go from sk minus 1 to sk. This is just a variable name. All I want to say here is I can go to the next one in some fashion, okay? The only thing I have to adjust maybe is like the starting point for this thing. The starting of the first one, it should never be below the first rung, because if I need to convince you to get that, in order to get to S2, I need to start at S0, something's fishy about that. Like there's no S0 to speak of, right? So it really should always be incremental, although we'll see some ways to advance that later. Okay, so I hope I convinced you that this actually holds, at least metaphorically, and it does in general. I don't want to prove it any further than that, except to say that there is an easy contradictive proof of this as well, right? Suppose 1 and 2 held, right? Suppose rules 1 and 2 held, and yet not all the statements S1 up to S infinity were true, right? That would be a contradictive setup here, right? Is it possible that the trillionth rung cannot be reached despite the fact that 1 and 2 hold? Well, no, because imagine I can't reach the trillionth rung, right? What would that mean about the rung just before the trillionth? I can't reach it because if I could, then 2 would say, oh, then I could have reached the trillionth. So if I can't reach the one before the trillionth, I can't reach the one before that. And before that, just repeated applications of 2, just say, oh, I can't get to the one before that, before that, before that. Eventually, tracking that all the way back down to the end, I can't reach the second, which means I can't reach the first, right? But 1 says I can reach the first. I started with the information I can reach the first, and I just proved that I can't. So this has to hold. There's no choice, okay? All right, so let's put this together to do the proof of this thing here. Okay. Now, for those of you in my Intro to Proofs class, we tend to be very verbose and careful. That is not going to happen this evening, okay? Yeah, so some of these will go a little bit quicker. They will all have a common theme to them. And with the algebra and some of the little details, I'll be asking for help, okay? And not just for pedagogical reasons, because like literally I will need it on the spot here, okay? So, all right, so let's write this out. This first one I'll be maybe a little pedantic with, but after that, less so. Okay. Yeah, actually, that's definitely pedantic with the first one so that you see the standard, sort of professional format of an induction proof. Okay. All right, so I'm going to call this a theorem. And I'm actually going to say for all n that are natural numbers, well, I don't like to, I'll say we have this. Okay, that 1 plus 3 plus 5 up to 2n minus 1 equals n squared. That's our statement there, that for every natural number n, this thing holds here. Okay, and let's start proving it. All right, here's a proof. I will only write this time that the proof will be by induction, but anytime you write an induction proof, tell your reader the proof is by induction. Okay, so we proceed by induction on the variable n. That's the only variable we'll speak of anyway here. Okay. Now, in order to prove that a statement holds by induction, I need to confirm the 2 bullet points in this thing here. I need to confirm that the statement holds for n equals 1. There must be good comments in the chat, Ryan. Okay. I've been watching it, so I know what can happen. But all right. So, no, it's all good. No. So I need to confirm it works for n equals 1, which we've already done. And I need to also confirm that if I assume sk, I can go to sk plus 1. Okay? And in this case, I'm gonna go with those variables here. Okay? So what we typically say is, for the base case, that's this bullet point 1. We call that the base case. It's the initial step. It's the first rung of the ladder. Some people call it, I think I read it called like anchor step once in another textbook. I see a nod there. There's many different ways of talking about it. N equals 1. I need to confirm that the statement of the theorem holds for n equals 1, right? What is the statement of the theorem for n equals 1?
That 1 equals 1.
It's literally that 1 equals 1. So as 1 equals 1, the statement holds. Base cases are always difficult to write down because it's sort of an absurd thing to write. We will see some examples later where the base case is not easy. I've been promising my proofs class that. We will have a couple tonight. But yeah, so here that was easy, right? Okay, so now we're going to try and confirm step 2. Okay, so what I'm going to say is let's let k be greater than or equal to 1. Okay, so I'm introducing this intermediate variable here. I like to think of this part as like a subroutine to this proof here, that I'm introducing a variable just to work in this part here, but you can still talk about n if you want, if you're comfortable that way. I tend to prefer it, and I'll probably use it after this, but okay. So we let this, and we're going to assume that the statement of the theorem holds for k, right? That we have sk, okay? So, and assume the statement for, let's say n equals k. I'll put it this way, okay? I'll just say statement holds for k. In other words, what is the statement for k? In this case, we literally just plug in k for n throughout the thing there, okay? So 1 plus 3 plus 5 plus 2k minus 1 equals k squared, okay? And I would like to establish the equivalent statement for k plus 1. What does that look like? It looks like everything here, a 2k plus 1 after it, and then a k plus 1 squared, okay? You may notice when we did the example, we had something with n minus 1, and we used that to establish it for n. This is no different. I have a new variable name here. I'm going from k to k plus 1 instead of n minus 1 to n. But if you set k equal to n minus 1, they'll be identical to each other, okay? Okay, now, how would I prove the corresponding statement for k plus 1 using this? Well, why don't we write down the left-hand side of the desired equation. So 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. Let me put these in parentheses just to emphasize. Those are sort of individual terms in the sum, right? This is the kth odd number, and this is the k plus first odd number. Okay? What do I want this all to equal? K plus 1 squared. Can I write k equals k plus 1 squared? No, not yet, right? I don't, like if I could do that, then I'd have the theorem, right? But what can I put here, Thomas? Do you know what I can use? Yeah. It was Keith, I know, but so I can plug in for this part here, right? The inductive hypothesis, that's what this is called, this bonus assumption, is this piece here, okay? That's k squared. right? So that this, I'll even recall it here, we usually don't write that down in the proof explicitly, but that is substituted for k squared because of this piece of information here. What am I missing though? Like this is not equality here. Yeah, don't forget this term here, right? 2k plus 1. Oh, and this one's really nice. In the previous example, we saw some cancellations and things worked out. What happens here instead? Yeah, is that what it's called? Yeah, like, like this is k plus 1 squared, right? Previously, remember we FOILed something out and things canceled? Here we had the opposite, but that's just because we went from k to k plus 1. There's no like difference in reasoning, it's just some different algebra comes out here. Okay, does this, what I just did here, does this confirm bullet point 2? It's exactly that, right? sk plus 1 followed from it. So now I have all the ingredients. I have the n equals 1, or if I want k equals 1, n equals 1. I have the n equals k, and from that I got the n equals k plus 1. So thus, by induction, the theorem, I don't know, holds for all n. Okay, end of proof. So the goal here with these induction proofs simply is to be able to have this recursive argument where it's like, you know, just repeatedly plug in forever until you get 1 equals 1. Like, we don't like to reason that way. This puts us on a formal grounding. But think about what's really going on here, again with the ladder, right? Here was 1 equals 1. Here was 1 plus 3 equals 4. How did I know that was true? Well, I used this to help me. It didn't help that much, but. And then how did I get here? This was 1 plus 3 plus 5 equals 9, right? And knowing this could help me get here and so on and so forth, okay? But I don't want to do these over and over again, especially if what I'm trying to prove is in general, all these equal n squared. Like how am I going to substitute in all the way back down? Like it will be horrible to write down. In fact, it's basically impossible. I don't know of a way that would be convincing. Okay, so now we have this rule in hand. We have to confirm the base case, we have to prove the next version follows from the previous version, and then our theorems are proved. So, let us do some, okay. Let's do a bit more interesting one already, okay? You guys have seen that one that are in my proofs class, so let's do this one. This one's cool, all right? There's only so many, and I want to cover the really cool ones later, so yeah. And if we have extra time, we can always go back to the easy ones, but. Okay, so let's try and figure out this one here. So what do we have here? We have these weird fractions. 1 over something, 1 over 1 times 2, 1 over 2 times 3, 1 over 3 times 4, all the way up to 1 over n times n plus 1. So that could be like 1,000 times 1 over 1,000 times 1,001. And all that put together equals n times n over n plus 1, right? Which is like, okay, maybe it's believable. I mean, I don't really know. Like the two sides have a quite different flavor to one another, okay? But let's see if we can convince ourselves this is true. I will no longer be writing down theorem statements or problem statements. So we're just going to prove this thing holds, okay? Now, I didn't say the values of n that this should hold for. We could check what makes sense for n's here. Are negative numbers reasonable here? Probably not. I'm just going to not deal with negatives at all. What n can I almost certainly not use here? Yeah, 0 would be really dangerous because the final term there is a 0 times n plus 1. So let's start from n equals 1. That's the only place we can really make a reasonable statement, right? Okay, so the base case is when n equals 1. And what I want to do here is just confirm that the left side and the right hand side do indeed equal each other when n equals 1. Which of the two sides are easier to parse when n equals 1? Yeah, the right side is like just some fraction, right? So the right-hand side is 1 over 1 plus 1, right? Did I get it right? Yeah, I got it right. 1 over 2. The left-hand side, when n equals 1, how many terms will be in that sum? It's just one term. It's not the easiest thing to see there, but when n equals 1, the 1 over 1 plus 2 is literally the entirety of the thing there, right? So the left-hand side is 1 over 1 times 2. This is equality, of course. Notice it's not quite as simple as the previous. Last time we had 1 equals 1, literally. Here we had 1 over 1 times 2 and 1 over 1 plus 1. I mean, yes, 1 plus 1 is 2, but like we did have to do something. Okay, so base case is confirmed. That's easy enough. Okay, so now I'm going to assume the statement for, I'm going to assume the statement is true for n minus 1 and try to establish that exact formula for n. I think that's a little bit more elegant. The last line of our proof will literally be that statement, and then we'll be done by induction. So assume the statement for n equals 1. N equals 1. We proved that. Let's assume the statement holds for n minus 1. Okay? Let's try and write that out. So the left side is going to, well, let's start with the right-hand side again. What's the right-hand side of this statement here when we're working with n minus 1? Yeah, perfect. N minus 1 over n. It's just the previous there. You just literally plug in n minus 1 for n is kind of how you do it. Just, as a rule of thumb, don't write this though. There's a tendency to do that, but like this, you don't want to do that, right? Like don't just say the statement for n minus 1. All right, anyway. What's the left-hand side? It's going to be, well, the first terms will be the same. 1 times 1 over 2. 1 over 1 times 2. 1 over 2 times 3. 1 over 3 times 4. This is like a crutch, you can just keep writing these for a while until you like start to see what should go on. But what will be like the last term here?
1 over n minus 1 times n.
Yeah, 1 over n minus 1 times n. Exactly, Russell, right? So 1 over n minus 1 times n. Everybody agree that's the term we should get at the end there? So that's the thing that we're assuming. I would like to use this in order to prove that. Okay? Now, I already want to introduce a wrinkle. So last time, how did we prove this? Well, it was a different formula. We looked at the left-hand side of the equality there, used this to plug in for most of it, did a little arithmetic, and then arrived at the right-hand side, right? I want to do something different instead. This time, I have this statement that I've assumed here. Instead of using this to substitute, I'm going to manipulate this inequality directly. Okay? So it's basically the same algebraically, but it's a little bit different approach. Well, this is an equality. I can add things to both sides. I can multiply both sides. I can manipulate both sides in the same way. What can I add to both sides of this so that it will look more like the thing we want to prove?
1 over n times n plus 1.
Very good, Daniel, yeah. So add 1 over n times n plus 1 to both sides of this equation. Okay. Well, then what do we get? The left-hand side literally becomes what we want, right? This plus this plus this. Everybody agree that that's the term like just before the last inside the dot, dot, dot? Like I don't see it, but that would be the previous term, okay? So this is just 1 over 1 times 2 plus 1 over n minus 1, I'll write it here, over n, plus 1 over the thing we added, n plus 1. Equals n minus 1 over n plus 1 over this thing that I added to both sides. Okay, so now I have my desired equation there. I've got the left-hand side of it here. What should happen to the right-hand side there? It should hopefully simplify to the right-hand side of the desired equation. Let's see if it does. Common denominator, it's got to be what we do here, right? So n minus 1, n plus 1, oh that's exciting, n plus 1, plus 1 over n plus 1. What's on the top of the left one there?
1, no n.
Yeah, so after we simplify, yes, we just get n. This, what I got excited about was the difference of squares. Like right, I love these ones. But if you FOIL it out, it's not important that it's a difference of squares. But it is n squared minus 1, and then plus 1, all over n times n plus 1. Yeah, n squared is left, not n, right? That's important here, right? And then these things, let me get a red just to emphasize better. These cancel. What else cancels?
The n and the n squared.
Yeah, the n squared and the n, and what's left? Radical. That's actually something I used to say in my youth. Anyway, so that's it, right? That's what I wanted. Okay? Everybody understand what I did here? It was a little different than before. I added to both sides instead of substituted. I could have just as easily substituted instead. I'm always trying to figure out which one's like better and shorter and easier, but I think it's just worth doing both. Van,
The camera got moved a little bit, so it's...
Yeah, it's slowly like, yes, getting worse and worse and worse, yeah. I'll let you, don't blind our audience. Here, while you're doing that, I will jump to the next one. Oh my God.
There you go. Sorry, folks.
I'll switch to that, and I'll erase. Okay. Okay. We good?
It's kind of charming. Yeah.
Kind of charming in a way.
The Johnsy can't.
Yeah, sure. Yeah, a kilter. All right, so this question, when I wrote this, was not, a few days out from March Madness, but it's actually quite apropos now. So I want to talk about single elimination tournaments, right? You got this huge bracket. Just think of March Madness or Wimbledon if you like tennis or any other knockout tournament. In order for these tournaments to work, you need a power of too many competitors, right? In each round, half the competitors are knocked out, and then half, and then half, and then half, until you have one team left at the end. So they're of the form 2 to the n, and n will be the number of rounds that you actually have. March Madness has 64 teams. Well, it's a little more complicated than that now, but let's just focus on the 64 teams. And they'll play each other out in that way until there's a single winner. And I want to ask a question here that's going to motivate the next slide, that in a tournament like this, whether with 64 teams or 2 to the n teams, how many games are going to be played in that? Okay, there's a few ways to answer this. There's a really slick way, and then there's a harder way, but those will give us an answer here. What's the slow way, the careful way of figuring out the number of games that are played?
32 plus 16 plus 8.
Exactly, how many per round, right? There's 64 teams in the first round. They're paired off for 32 games, right? So let's write that, 32 in the first round. And after these games have been played, half the teams are left. There's only 32 teams left. And 16 of them there's 16 games to be played. And then you get 8, right? And then 4. This is the Elite 8 point. And then with, wait, what? What am I counting here? Teams, I'm counting teams, right? Or what am I playing? No, I'm counting games. So then this would be the Elite 8. There's 4 games with 8 teams. Final 4, final. What? Yeah, okay, that's the answer, whatever. I'm not gonna use terms. Okay, I got a thumbs up. All right, what does this add up to? 63. Yeah, 63, right? What's the clever way of determining the number of games?
2 minus 1.
Yeah, okay, so Russell, that's the more general format, right?
The game knocks out exactly one team.
Yeah, so the clever way is, in every game, a team loses, right? Who cares what round they're in? First round, last round, every game a team loses. Every team loses except for the champions. The champions never lose. So if 63 teams lose, how many games are being played? 63 have to be played, right? Like literally, there's no way to escape it. You can't have 2 teams lose a game, right? So 63 have to be played, right? So you can get here directly without adding these things up. So actually, what we just argued is a proof that this equals 63, but not a very interesting one because you can just do it on your calculator. But it does prove something more general. And what Russell highlighted was, okay, what if our tournament has 2 to the n teams, right? How many games will be played in round 1? If we have 2 to the n teams. Yeah, perfect, 2 to the n minus 1, right? 2 to the n divided by 2, right? The teams are paired up. In the next round, 2 to the n minus 2. In the round after that, 2 to the n minus 3. And we keep going down, eventually we get the same thing, 4, 2, 1. Maybe to keep it consistent, it's better to write it as 2 to the 2 plus 2 to the 1 plus 2 to the 0. But on the other hand, if the tournament had 2 to the n teams and there was a champion at the end, how many games were played? 1 for each loser, 2 to the n minus 1. The minus 1 is down here. It couldn't be up there, obviously, right? So we didn't even need induction to prove this. This just follows from analyzing tournaments, right? So I want to prove by induction something more general than this. This argument that we've just given here we've seen a few, this is called a double counting argument, right? We figured out the number of losses in 2 different ways and established this cool formula. What is this cool formula? Look what it says. It says if you add up the powers of 2, 1 plus 2 plus 4 plus 8 plus 16 plus all the way up to say 512, what do you get? You get the next power of 2 minus 1. You just come up short by 1, right? So if you add up all the powers of 2 up to 512, what will you get?
2 to the 511 minus 1.
No, I didn't mean 2. I didn't mean 2 to the 512. That's a good point. 1,023, right? 2 to the 10, but minus 1 previous. So there's a nice shortcut for these things. It's actually really cool. I don't know, there's sort of like something, I don't know, like depressing about it, or I don't know how to describe it, but there's this feeling that like you add up these powers of 2 and you always just come up short of the next one. And if you add this one onto it, you still come up 1 short of the next, like you could never reach the next power of 2 by adding powers. I mean, it's just because you have this equality here. Okay, so what I would like to prove here, and I know this is, again, familiar to my proofs class students. I think we like literally did this yesterday, maybe? Yeah, okay, so we should still do it, but I want to prove a more general formula here. We just proved this formula for r equals 2. You guys see what happens if I plug in r equals 2 to this formula? I get 1 plus 2 plus 2 to the 2 plus 2 to the 3 plus all the way up to 2 to the n. And the right-hand side doesn't quite look like it, but look carefully. It's 2 to the n plus 1 minus 1, so the next power of 2, but divided by what? Just 1, fortunately, right? In this case, when r is 2, 2 minus 1 is 1. The division part just kind of vanishes. It's not important, okay? So, as I told the proofs class, this can be proved without induction. This is a cool multiplication and telescoping thing to prove it. There is also an extremely clever way to do this by thinking about tournaments as well, but it's a little more complicated. In tournaments, you have 2 teams, one gets knocked out. How would you build a tournament where there's like R teams playing at once? There's some way to do this, okay? But I'm not going to do that. We're going to do it by induction, okay? So let's prove it. What's the base case? Okay, even better. What are we doing induction on? Yeah, it's a good, I know it's not a guess, but like, I didn't even say what n and r are here. And in fact, there's a problem that's not articulated here at all. R better not be 1. You can't divide by 0, but you know, who cares about such subtleties, right? It's like, we'll not worry about that. Okay, so it's induction on n. When n equals 1, what is the claim of the statement here? Well, 1 on the left-hand side should equal, hopefully. The right-hand side is what? R to the n plus 1? Wait, oh.
You want to start at 0.
You have to start at 0, thanks. That's better. Let's start at 0. If we start at 1, it'll still work, but I should take the r and r plus 1 terms. Actually, it's quite nice, it works out too. But it's induction where we start at 0. Okay, interesting wrinkle. In the previous 2 examples, we started at n equals 1, right? Remember our ladder? You start at the first rung, go to the second rung, and go on. You can start at 0 if you want. Just rename the ladder, and you have a 0th rung is your base case, okay? So I don't care where the base case starts. I just have to have a starting one and always show that I can get to the next, okay? All right, anyway, so at n equals 0, yes, then indeed the left-hand side is just the 1, because the r term doesn't appear. That'd be an r to the 1. And the left-hand side would then be r to the 0 plus 1 minus 1 over r minus 1, which cancels and is indeed 1. Okay, I'll just leave it as this. Base case confirmed. Okay. What's the inductive hypothesis? Let's sum up to the n minus first power. What will this equal? What power here? Just n, right? n minus 1 plus 1. Okay, so I'm allowed to use this formula, and I want to use this to establish that formula there. Let's add r to the n to both sides. Same exact strategy as before. Okay, if I do that, then this becomes what I want. Right, if I add r to the n to both sides, it gets r to the n minus 1 and then r to the n term. And the right-hand side, less obvious, but r to the n minus 1 over r minus 1, and then plus r to the n. And how do I finish this one? Actually, it's almost identical to a few slides ago. Find a common denominator and work the algebra. Let's do that real fast. So r minus 1, r minus 1, r to the n. Put these together. You have everything over r minus 1, and then you have r to the n minus 1. What happens with this guy here? You can multiply it out. Actually, you can already see that it cancels, but let's multiply it out anyway. What did I do wrong? Nothing wrong. R times r to the n gives me plus r to the n plus 1, and then I get a minus r to the n. All right? And look what happened. Things canceled. And I'm left with r to the n plus 1 minus 1 over r minus 1 QED. Okay, so these are all the same so far, right? There's no new ideas here. It's just plug in, add to both sides, do arithmetic, and if you don't make any mistakes, it works out every single time. Okay? So let's do something other than this. And let's not do this. Keith gave us this proof on Friday. I won't ask him to come up here and do this. Let's do one that's actually turns out to be much easier. So, whoops. Let's prove an inequality instead, okay? Still not too much of a brain buster, but I promise you we'll get there. So how about this one? Actually, this one, while easy, is very interesting, right? 2 to the n, the exponential function 2 to the n, grows very quickly, right? It beats all polynomials. We've seen throughout the hours here that even things like 2 to the 100 are hilariously big, right? They're like enormous numbers. But I'm claiming that it's always losing out to n factorial, at least eventually, right? For the first few values, for instance, n equals 3, the left-hand side gives you 8, and the right-hand side gives you 6, so it doesn't hold. But for 4 and beyond, it begins to hold. Okay? So I would like to prove this by induction. So let's switch back over. And base case. What's the base case here? Again, a wrinkle. Yeah, we have to start at 4. We've only claimed the theorem for 4, right? And it doesn't hold before that, okay? So at n equals 4, that's the first instance. That's where our ladder actually starts. The left-hand side is 2 to the 4, and the right-hand side is 4 factorial, right? And this is, what, 16, and this is 24? Great. It does work, okay? Hey, Hannah. Okay, so what's the inductive hypothesis? Let's go from n to n plus 1 this time, just to mix it up, okay? So let's assume that 2 to the n is indeed less than n factorial. And just since we're doing a little bit different model this time, what do we want to show? If this is what we're assuming, what's the next thing?
2 to the n plus 1 is less than.
Yeah, 2 to the n plus 1 should be less than n plus 1 factorial, okay? That's what I'd like to establish. Okay. Well, why don't we do the following? Let's multiply both sides of this by 2. So 2 times 2 to the n is less than 2 times n factorial. Be very careful. This is 2 times n factorial, not 2n factorial, which is a much, much larger thing. Although, you know, it would still hold. It just wouldn't be proper reasoning. 2 to the n plus 1, less than 2 times n factorial. What do I actually want, though? I want this, which is less than this. I want it to be less than n plus 1 factorial. Is it? So let me write what I want here. I would like for this to be at most n plus 1 factorial. How do I get from here to there? Well, this is n factorial times 2. What I wrote there was n factorial times n plus 1, right? N plus 1 factorial is literally n plus 1 itself times n factorial. I actually remember that this was on one of my factorial arithmetic slides, like literally 12 hours ago, and I did not solve it. But of course, it just follows from the definition. This has all the smaller terms. Multiplied by this just gives all these terms here. It's just, you can break it apart there. Okay? Well, here I have 2 times n factorial, and what I really want is n plus 1 times n factorial, because this would be equal to n plus 1 factorial. Right? This is less than this, hopefully is less than that, is equal to that. I would have the chain of inequalities. Is the question mark true? What am I actually asking in disguise about that question mark term?
Is 2 less than n plus 1?
Yes, is 2 less than or equal to n plus 1? Is it? Yeah, we have to be a little careful because I went from n to n plus 1, it's a little tricky like what the actual value of n plus 1 is. But n is at least 4 in the first place. So at worst, maybe like you might worry that this could be 3 or something, but whatever it is, it's definitely bigger than 2. Okay? All right. Yeah, maybe this was not the best example to decide to, on the fly, go from n to n plus 1, but it still works, certainly. Okay. How about, okay, cool. Hopefully derangements are somewhat fresh in your mind. If they're not, we'll recall a theorem here that Van proved for us. Okay, so I want this lower bound on the number of derangements, okay? What's the obvious upper bound of a similar flavor on the number of derangements? Anyone care to guess? Like yeah, Van.
N factorial.
N factorial. There are n factorial permutations. Some of them are derangements. Well, I shouldn't say most of them aren't. Most of them,
Less than half.
less than half of them are, but yeah, okay. So well, I'm not going to use that. I'm not going to use the upper bound either. It's just something I want to remark on. I'm interested in the lower bound. There's at least n minus 1 factorial derangements. For this problem, luckily, you don't need to know anything about derangements, except for the formula I'm going to tell you in a moment, okay? So let's try and figure this out. Okay, you have to know a little bit, but not much. Okay, I will ask Van for additional assistance here to prove this. So where should this be initialized? What n is the smallest for which this makes any sense?
2.
Yeah, 2. There's no derangements of one element, okay? I don't want to spend too much time on it, but if you permute elements in such a way that no element goes back to where it started, you cannot do that with one element. One element lands where it started because there's only one element. With 2 elements, you can transpose them and then they're mixed up, right? So n equals 2 is the only place this even makes sense. Okay, so the base case is when n equals 2. Okay? So let's look. D2 should be greater than or equal to, hopefully, 2 minus 1 factorial. Okay, luckily not that high of a demand. We just need D2 to be at least 1. What is D2? Van, you must have given D2 at one point. I literally, like, I cannot at all see, like, all I said was a middle finger, actually, was like, so I assume you were holding up one finger? Yes, but maybe not the middle finger, yes. There's only one derangement of 2 elements. Here's my 2 elements. There's only 2 permutations of them. This and this. That one's deranged, that one is not deranged. So 1 out of the 2. So this does equal 2, so it is indeed greater than or equal to 1. Okay, whatever. Inductive step. Let's say, for the inductive hypothesis that, what do I want to do? I want to go with dn minus 1 is greater than or equal to n minus 1, n minus 2 factorial, okay? That's the statement there. And what I want to show is what's written on the board there, okay? Anybody remember, and this time not Van, I wonder if anyone remembers, how many recurrences for dn did you show us? I know you skipped 1, but you must have shown at least 2 maybe, right? You did show the one I want. Anybody remember 1? By any chance? It did involve dn minus 1 and no other terms. Actually, I think I forgot it too. No, let me see. N times dn minus 1, and then had this really annoying part, right? You remember what it was, Ryan?
Plus minus 1 to the end.
Yeah. Like this is not a good recurrence. I mean, it's like way cool that this is a recurrence, but it's not nice to work with because it's like, oh, sometimes you add 1, sometimes you subtract 1, like it's weird, right? But for our purposes, it is potentially workable here, okay? Why is it workable? Well, Van gave other recurrences where there was a dn minus 1 and a dn minus 2. We don't know how to deal with that yet. We will soon, though, okay? All right, so let's use this. Okay, so dn equals, well, it's literally written there. I'm not going to write it again. How can I use induction on this to help me? Think substitution, right?
I think there's a, like, you can move dn minus 1 so it's equal to, like, dn n plus negative 1 to the n, something like that.
Wait, oh, Thomas, you're suggesting like solving for dn minus 1 essentially?
Yeah.
Okay, I think that could potentially work. But instead what I'm going to do is just, what am I trying to get? Ultimately, I would like to see dn is greater than or equal to something. And since I have dn already isolated here, I just need to put a greater than or equal to and write something out here that ultimately turns into n minus 1, right? I think what you're saying almost certainly will work. I may just have to rearrange terms after the fact, right? So which term in this thing here can I make a substitution for? dn minus 1, right? I know it's greater than or equal to something. So let me replace it with this thing here, which I hope you'll see will put the inequality in this direction. So I'll have n times n minus 2 factorial, and then plus negative 1 to the n, which I really hope I can get rid of somehow, right? Now this is a little strange. N times n minus 2 factorial, there's no like good substitution for that, unless I just decide to do this. What if I rewrite it like this? I'm going to split n into n minus 1 plus 1, okay? Cameron, one of our former grad students, taught me this idea of a fancy 1. That's when you multiply something by like 7 over 7. That's a fancy 1. Here I'm adding a fancy 0. What's a fancy 0? It's plus 1 minus 1. They cancel each other out. Okay, maybe I'll write it because I think it's so fun. So n minus 1 plus 1. That's like literally just n there. And then n minus 2. This is a common little math trick. I didn't change anything. I just introduced this. But what I want to do is now I can FOIL this out with this guy in a way that's convenient for me. I mean, not fully FOIL it out. Just, what do you call that when you multiply 2 terms by 1 there? There's a rule for that. Not distributive, thanks. Distributive is what I was looking for. I don't want to FOIL through this thing, right? Like necessarily, right? So, okay. I'll have n minus 1 times n minus 2 factorial. Oh, wait. I mean, this works, but okay, yeah, why not? Plus n minus 2 factorial plus negative 1 to the n. I think this will work. Yeah, okay, that's not what I was expecting, but you know, whatever. What's this? N minus 1 factorial, right? Okay, there's something left over, but I'm close. I've got dn is greater than or equal to this plus some chaff, right? That circled part, if it's what, will I be safe? As long as it's not something, then I'll be done. It shouldn't be negative. If it's 0, actually things will just fit together. If it's negative though, then I'd be saying dn is greater than or equal to n minus 1 factorial minus something. It's like, well, I'm trying to prove that it's at least, oh, it's on the screen, right? As you guys can see. So hopefully I want this thing to be at least non-negative. Is it non-negative?
Yes.
It is non-negative, right? So what's the worst that this thing can be? Minus 1. It depends on the pair. It might be positive 1, and then it's great, but it might be negative 1. But what about this? What's n minus 2 factorial? It might be small.
Is n equals 2 our smallest, so it's just 0?
Yeah, I think at this point it might potentially be n minus 1 has to be at least 2. That's our previous case. We can't go before that. So this n is at least 2. Minus 2 is 0. 0 factorial, though, we learned very early on, is 1. And so we have a plus 1 and potentially a minus 1, maybe even a plus 1.
Well,
but
in that case, it's a plus 1.
Is it? I mean, what if n was 7?
Right, but
Oh, I see what you're saying, Thomas. Yeah, that's actually nice. Yeah, at that very edge case, we have a little wiggle room. If n was 2, this would end up being a plus anyway. Yeah, okay, so if you're uncomfortable with 0 factorial being 1 and you want it to be 0, this is probably not helpful, you guys. You get a plus 1 from this, okay? Independent of this works, right? So I proved dn is greater than or equal to n minus 1 factorial, okay? And we use that recurrence. Okay. Now what? Oh yeah, all right, this is a good one. Good. You guys recognize this thing? The harmonic series? Truly hated by many a Calc 2 student, right? It's like, shouldn't this like add up to something? And it doesn't, right? It gets infinitely big. And probably they proved why in calculus, and maybe you were unconvinced. It took me a very long time. In fact, this proof is what convinced me, oh yeah, it clearly gets as big as you want, okay? So let's prove that this gets large, and we'll do it by induction, okay? So I again, 12 plus hours ago, I talked about how there are some connections of discrete math to continuous mathematics, and here's one instance where it comes up, okay? All right, so I want to show that this diverges. How do you show that an infinite sum diverges? What does that even mean? It means that if you add it up, it goes to infinity, but like infinity is not a number. It's hard to talk about it adds to a specific value. What's a better way, like what's a witness for something going to infinity? Right? That's an infinite sum. If I were to add all the terms up, I'd get infinity. I can't really do that, but do you guys remember partial sums? If I add up the first 1 million terms of that, what do you think the first 1 million terms of that add up to? It's, Russell, that's a good guess, actually. Ryan, if you ask, I think if you literally ask Wolfram for the sum of the first million terms of the harmonic, it'll tell you a number. I'm just curious. I think you might not be far off. And actually, we'll see kind of why in a moment. Do you know, Russell, or was that a bona fide guess? Okay, that's awesome, yeah. So what we're gonna show is that if you give me a number, like 100, I can say, oh, if you go far enough, you'll go above 100. Or you're like, okay, 1,000. If you go far enough in this sum, you'll go above 1,000. No matter what number you give, I can go far enough in this sum that I go above it. If that's true, can this converge? No, like tell me a number it converges to, I can keep adding and go above that number. So it just goes to infinity. Okay, that's what it means to diverge. There's other ways to diverge, but that's the way it goes to infinity, that there's no number that I can stop it by. Okay? All right, so what I want to do then is show that I can make this sum as big as I want here. Okay? But it requires a little bit of analysis to figure out how to set this up. So what's the best way to go about doing this? Yeah, let's think. What?
It's about 14.
Oh, 14, okay. 100 is still not a bad guess. 14, really? So I know it grows about log. What's log of a million?
Yeah, about 6.
6, okay. all right, anyway, so cool. Oh, that's so way cool. Okay, but actually that tells you something really interesting here, right? So I claimed that this will eventually exceed 1,000, or any number you give me. But it took 1 million terms to get above 14. Right? So getting above 1,000, like it happens, but it takes forever. But it still gets there. Why does it take forever? Well, each term you're adding, they're getting smaller and smaller and smaller and smaller. Right? By the way, do you guys remember what's the value of the, okay. If you look at the Wikipedia article for harmonic series, it's amazing. There's like so many cool things. But in Calc 2, why do they teach you this thing in the first place? Anybody remember? It's a gotcha. It's a gotcha problem. Right, for a very specific thing. What is your first intuition about infinite sums and convergence? Yeah, your first intuition is that if the term 1 over k goes to 0, then it should converge. That's what you think at first, right? Everyone thinks that at first. And then, your calculus professor taunts you and says, yeah, this one doesn't. This diverges, despite the fact that the terms get smaller and smaller and smaller. Okay, anyway, all right. So there's no statement yet to prove, right? So instead, what I'm going to prove to you is that for any number, I can take enough terms so that I exceed that number. And in fact, I'm going to write it in the following way. I'll just spoil it instead of trying to arrive at it. So I'm going to claim that if I take the terms I equals, did I index this from 1? Yeah. Oh, k equals 1 over k to something. We'll figure out in a moment here. This is at least 1 plus n over 2. N, not k. N is something else. This will be this, okay? So I'm gonna write this as a theorem, okay? I think that's an N. Okay?
Is it proved by theorem?
Yeah, it will be proved by corollary of this theorem, yeah, very good. Yeah, so this is the theorem I intend to prove. Let's look at why this would prove that that guy diverges there, okay? Let's try and unpack what this says, okay? So what this really says is for all n, at least maybe 1, I don't know, that if I take the first 2 to the n terms in the harmonic series, so the first 16, 32, 512, and add those up, I will get a number that's at least 1 plus that very same n that was up here divided by 2, okay? So for instance, if I set n equal to 10, this theorem claims that if I add up the first 1,024 terms of the harmonic series, I will get a number that's at least 1 plus 10 over 2. I'll get at least 6. Okay? Actually, we heard from Ryan that that's what? Does that match up with what the computation told me? Oh, I asked for the log of something. Yeah, never mind. I didn't ask for this exactly. Okay.
Maybe log base 10, not log 3.
Oh yeah, okay, that's the other thing. Sure. Okay, there's no log here anyway, I'm just sort of riffing a little bit, all right? So do you guys see that if I want to convince you that the harmonic series goes above like 50,000, that this would tell me? How would I figure that out? How would I know which n, how many terms I have to add up to get above 50,000? I'd need this number to be at least 50,000, right? And if this number is at least 50,000, then by the theorem, this sum is at least 50,000, right? Okay, well, if I want this to be 50,000, what does n need to be, just roughly? Oh, yeah, thanks, Heath. About 100,000, right? 100,000 divided by 2 gives me 50,000. This gives me a little more, but about 100,000. This would say, how many terms would I have to add up to get above 50,000? Yeah, be careful. Not 100,000 terms, but 2 to the 100,000 terms, right? K equals 1 up to 2 to that 100,000. 2 to the 100,000 terms. Think about that number. Okay, but whatever, I'll get above 50,000. Say I want to get above 1 million. Then I need to go to the 2 to the 2 millionth many terms, okay? But do you guys believe me now? At least if I can convince you of this, then this thing does go to infinity. There's no number, I can always get it as big as I want if I sum it out far enough, okay? Anyway. All right. So let's try and prove this theorem instead by induction. What's the base case? Let's see what it looks like at n equals 1, okay? At n equals 1, and if it's wrong, we'll have to make a slight adjustment too. That'll be a thing here. When n equals 1, the left-hand side will be k equals 1, or 1 over k, up till when? 2. Yeah, 2 to the 1, right? I'll put the 1 in there just to emphasize there. And this is a 1 here. And what is this explicitly then? This sum has 2 terms in it only. And it's literally 1 over 1 plus 1 over 2. Okay? I haven't tried to compare it to the right-hand side. That's just what it is there. Okay? Oh, I think it works though, right? But when n equals 1, what's the right-hand side, which we claim to be larger, smaller? 1 plus n is 1 over 2. Ooh, it just fits, just perfect, okay? At n equals 1, we actually have equality. Okay, but that's okay, I have greater than or equal to here. All right, so the base case works. All right, now let's do the inductive step. I think it will be nicer if we go from the statement for n, which is written here, to the statement for n plus 1. That's what I think. So let's try that. So what I'm going to do, this is sort of cheating, but I'm going to assume this statement's true and try to establish the corresponding statement when n is turned to n plus 1. So what I want is this sum here, k equals 1, up to 2 to the what? 2 to the n plus 1. 1 over k. And let me write it, but I'm going to erase it in a moment here. I want this to be greater than or equal to what?
1 plus n plus 1 divided by 2.
Yeah, perfect, Thomas. N plus 1 divided by 2. That's my goal, right? Yeah. Notice something. That's my goal. I don't know that's true, but I'm going to work with this thing to get it. Notice what happened. On the left-hand side, how many more terms are here compared to here?
2.
More than 2. Double as many, right? This goes up to 2 to the n plus 1 many terms. This is 2 to the n many terms. This number is twice as many as this number, right? What's the difference between the right-hand sides, though?
Plus 1/2.
Yeah, just a measly 1/2. It doesn't even depend on n, right? So I doubled the number of terms and gained a 1/2 only, okay? All right, but we don't know this. We want to prove this. Okay, so I know my inequality should be in this direction. Let's write equality first and do the following. Let's split this sum up into k plus 1 up to 2 to the n, so the first half, and then the rest. So this is k equals 1 up to 2 to the n, 1 over k, plus the rest of the terms, 1 over k, 2 to the n plus 1, k, what's k equal here? So think about this sum. This goes k equals 1, 2, 3, 4, all the way to here. And all I've said here is start with 1 and go up to 2n, and then start at the next one and go up there. So what would this one be? with the, yes, perfect, Russell, yeah. 2 to the n with the plus 1 down here. That's the number after that number, okay? Everybody agree? All I've done was split that sum into two, like I broke it off in the middle, okay? What's the relevance of induction here? I can use it, all right? This thing here is literally my inductive hypothesis. So now I know that this is greater than or equal to 1 plus n over 2. I'll write it again, but plus this extra stuff I haven't dealt with yet. Okay, and just so we have an idea of what we need to do here, remember what I wanted. At the end, I wanted this entire sum was 1 plus n plus 1 over 2, right? I've already got 1 plus n over 2 accounted for. All I need to convince myself is that this is greater than or equal to what? 1/2, Ryan, yeah, very good, right? If this is greater than 1/2, then when I put it here, I'll get an n plus 1 over 2 instead. So this monster sum, right, there's a ton of terms here. I just need to show it's bigger than 1/2, okay? So that's what remains to do here. All right, so let's write that up over here. I want to just analyze this sum. This is like its own lemma here, okay? So now I've got sum k equals 2 to the n plus 1 up to 2 to the n plus 1 over k, okay? And I want to find what this is bigger than. And then I'm going to plug it in here. I'm hoping you get a 1/2, okay. All right, so if you're estimating a sum from below, Russell. Oh, thank you. Yeah, this is vital here. Dang it. All right. Perfect. Can you see the screen from here? Yeah, okay. So yeah, continue to call it. Just like this mic makes it hard for you guys to be heard too much if I'm talking. So if you guys yell out screen, like the stream probably won't hear it. Maybe they will, whatever. So, okay. So I have this large sum here, and I want to do a really, really crude lower bound on it, okay? So say you have a sum, and the terms in the sum are decreasing. Everybody see this? 1 over k is getting smaller and smaller and smaller and smaller. What's the dumbest lower bound I could put on this thing? Okay, not the dumbest. Don't, Daniel, you have an idea?
0.
Okay, I don't want to say it, but slightly less dumb, let's say. But yeah, I'm not being nice, but yeah, we want 1/2, right? And so when talking about a sum, instead, let's say, what if I just replace all the terms in the sum with the smallest term that appears, like the one that appears at the very end? I know they're all at least that one, right? What's the smallest term in this sum? Indeed, the last one. What is its exact form?
1 over 2 to the n plus 1.
Yeah, 1 over 2 to the n plus 1, right? So I could instead add up a bunch of 1 over 2 to the n plus 1s. I'd be making a sacrifice, right? Because the one before it's a little bit bigger, but that's fine. So that'll be 1 over 2 to the n plus 1. But I don't want to replace this sum with a single term. I have a lot of these. How many terms are in the sum? That takes a little bit of work, but how many terms actually appear in this sum? Yes, so it would be, it's actually this amount minus this amount plus 1. But actually the easier thing to do, I think, is I split these two sums in half at the middle of, I split this sum in half at the middle. And so there's as many terms here as there are here. This one's a little harder to analyze, but this one, there's obviously 2 to the n terms. I start from 1, go to 2 to the n. This is the remaining half. There's 2 to the n terms here exactly. So 2 to the n terms, all of which are at least this smallest quantity there. What does this equal? 1/2, right? So of course, this is bigger than 1/2, but that's fine. It's certainly greater than or equal to 1/2. And so now, down here I have this is greater than or equal to 1 plus n over 2. Just as a sanity check, where did that come from again? That was the magic of induction, right? That was the black box. I got that for free from this thing here. And then I got an additional at least 1/2 from this. Probably more, but at least 1/2. So this is at least 1 plus n over 2 by induction plus 1/2. I analyze this to be this. And this is 1 plus n plus 1 over 2. End of proof. Okay? Yeah. There's another way to visualize this that I'm not going to do, but if you write out lots of terms and look at like long chunks of length powers of 2, and then replace them with their smaller terms, you get a bunch of sums of powers of 2, and those have a nice behavior as well. Well, those are in denominators. I have to do a little more than that, okay? Anyway, that's the inductive proof, okay? What do you guys think? That's pretty cool, right? Look at this, look at this. What if, now that I have this formula, let's rewrite it in a way that's a little easier to parse and gets at something I was hinting at here. Let's put m equal to, what do I want this to be? Let's put m, okay, m equal to 2 to the n, okay? So let's say that, this is a substitution here, all I want to make. So then this sum would become the sum from k equals 1 up to m, 1 over k. Now m is technically hidden, it's of the form of power of 2, but let's just, not worry about that for a moment. This is greater than or equal to 1 plus, well, I want this in terms of m now. What is m in terms of n? What I'm asking is, how do I solve that for, for n. I want to solve that for n. Yeah, I want n in terms of m, so I can make a substitution here. How do I solve that?
Log base 2 of that.
Yeah, exactly. So log, sometimes they use LG for log base 2, I think, of m equals n, right? So that means over here, instead of n, I have log m, and I'll say 1/2 in front there. So what this says is if I take this sum, 1 over k up to m, it grows faster than log of m, which, Russell, this is why I was interested, because if we take 1,000,000 terms here, it should be at least half of log of 1,000,000. So like that definitely dropped a lot. It dropped even more than we did. But this is actually a cool thing that doesn't always come up. The harmonic series here grows, this is just a lower bound, but the truth is it grows kind of like log m. When you add up these terms,
It's also like, it's like log of root of n, right?
yeah, this would be, I think the truth is maybe not root. I don't actually remember. This is just a lower bound, right? Keep in mind, we did give up some stuff, and so there is a better result. But as a lower estimate, yeah, I mean, actually, it's cheating to say that log m is a lower estimate, because it's not. It's something smaller, but yeah. Anyway, that's why I asked Ryan what was the log of 1,000,000 too, because I knew this in advance that there was some relationship. Okay, all right. All right, what's next? Okay, this is a new type at least. Let's do this one. Okay, it's easier, so that's good, right? And it's like sometimes they can't all be like this last one. So. All right. So I claim that 2n factorial, right, the quantity 2n, like 8, 36, 48 factorial, divided by 2 to the n, like spits out an integer every single time. So things cancel, this is never a fraction. It's some kind of integer. Okay, so this is a different flavor of the other ones. I'm not claiming something's bigger than something. I'm not claiming this summation works out to this summation. In fact, there's no equality or inequality to work with. There's no formula to manipulate. I just have this thing here, okay? Now, those of you that have seen some induction proofs, you've definitely seen divisibility type induction proofs. This is very closely related. This is saying something about divisibility in disguise, right? In fact, any of you that are in my proofs class now care to weigh in what this actually means in terms of divisibility? So if I divide something by something and get an integer, it means that the thing in the denominator divides the thing in the numerator. Yeah, it's not like 7 divides this thing. This says 2 to the n divides 2n factorial. It's like weird, but that is a thing, okay? Let's prove it. What do we have to do first? Base case, yes. Thank goodness for the base case. At least you can get some points, right? So, okay. Oh yeah, okay, I am missing something here, and we can figure this out on our own. Where should it start? Let's test some values, right? If I plug in n equals 0, say, let's not go negatives. In fact, definitely not, because we don't know what a negative factorial is. There are definitions of them, but. So if I start with 0, I have 1 on the top and 1 on the bottom, right? That works. So we can start there then. Let's start there. Okay, so n equals 0. Okay, and we just proved that it's an integer, right? For n equals 0, you have 2 times 0 factorial over 2 to the 0. This equals 1 over 1, which equals 1, which is an integer. Base case done, okay? If we wanted to start from 1 instead, it would have also worked, right? Then you would have 2 times 1 factorial. 2 factorial is 2, and you have 2 to the 1, which is 2. It actually would have given you 1 again. Okay, so now let's assume that 2 times n minus 1, okay, gotta be careful here. That factorial over 2 to the n minus 1 is an integer. Okay, that's my inductive hypothesis there. That's the previous case. Okay, maybe better to express this multiplied out so I don't have a bunch of parentheses. What's actually inside of the factorial here? This is 2n minus 2, right? Just so it's a little prettier like that way, yeah. Yeah, you never know if I'm going to ask you an easy or really hard question, right? It's like, anyway. So. All right, I want to prove that's an integer. So the nice thing about proofs like these, since there's no equality, there's no danger of like writing down what I want to show. Like I can just literally write down 2n factorial over 2 to the n, and like work with that and hopefully find that it's an integer. Like I haven't made any claim yet. I just wrote down some number here. Okay, I want to show this is an integer. I know that's an integer. What do you think might be a viable strategy here?
Show that there are n2s in the numerator.
Let's see here. Say that again, Daniel?
If you want to show that there are n2s in the numerator.
Of this one? Or, okay, I see. Yes. Okay, that's great, actually. If I could show there are n2s in the numerator here, then they would all cancel with these n2s. And you actually can do that. But notice, if I can do that, then I don't need induction. I just do that, right? That you can prove it that way. In fact, it's really easy. Okay, this is an aside. Let's do it real fast. Think about this 2n factorial. The first term is 2n, that contributes a 2 to the product. The second term is 2n minus 1, that's odd, that doesn't do me any good. The next term is 2n minus 2, which is even, which contributes another 2, which should cancel with one of these 2's. And you keep going down, and you're gonna get how many even numbers in this list when you multiply them all out? Or n even numbers, each of which contributes a 2, which can cancel with these. And then you have all the odd numbers still left over, and other stuff, but like, it's an integer. Okay, proof, great. We didn't use induction. Let's use induction. Actually, the inductive proof is essentially the same in disguise. This says that this numerator has n minus 1 2's in it, and we just need to find one more here, essentially. Okay? So let's do this. Let's write this factorial and this thing so that this thing appears, which I know is an integer, and then just deal with the leftover stuff. So how do I transform this into this? (2n) times 2n minus 1 times 2n minus 2 factorial, right? Everybody agree that's the numerator here? That's the first term, second term, and then the rest, which happens to be that. What should I write in the denominator to be useful for me as well? I mean, I have 2 to the n, but how might I expand it that's like more valuable?
2 times 2.
Perfect. Yeah, let's write it as 2 times 2 to the n minus 1. Right. Why did I do that? Because, what do I know about that? Yeah, it's what we want. We know that that's an integer, right? We know that's an integer. So like, I don't even care what it looks like. It's an integer, this circled thing, by induction. Okay? So I just have to convince you that that's an integer as well. Do you believe me that that's an integer? Are you shaking your head, Thomas?
Well, it's not completely obvious.
Okay, good, that's fine. All right. Yeah, sorry. Shaking the head is like has two possible meanings, that you don't believe me or that you're not convinced yet. Yeah. There's one quick change I can make to convince you that's an integer though. Anybody see it? Yeah.
You take the 2 out of the 2.
Yeah. Like, yeah, this is no longer part of a factorial. That's just 2n, right? So like literally cancel those two things with each other, right? Then I have n times 2n minus 1, but those are both integers, right? So I have integer, 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 lots of integer. Well, that's a big integer. So those of you in my proofs class, there's something called fact 2.3, right? And Russell, you remember too, right? That is that multiplying integers together give you integers, okay? What's left is an integer. I needed to cancel that too, though. If it's in the numerator, denominator, like, all bets are off, right? Thomas was absolutely right to be suspicious. Fortunately, it was easy to cancel, but it better be canceled, okay? Yeah. So actually, I would say this is like a pedantic version of what Daniel pointed out. Like, this is just, using induction to deal with the fact that the 2's cancel out here by magic. But if you wrote it out, you could just literally do this cancellation n times, and it would work out, okay? All right. That, and then that. Okay, yeah, I don't want to do that one. It's boring. We've done this too many times already. Van did a recurrence of this one. What, you think I should prove this? It's so lame. Okay, okay, all right, I guess it's been a theme. So, can I use your recurrence to prove, prove it? How about?
So the recurrence is that d sub n equals.
Yeah, I don't want to do that either. All right. But I mean, the proof that this is 2 to the n by induction is, okay, no, maybe it's not so bad. All right.
By fact 2.3?
No, I don't think by fact 2.3, so, yes. Okay, so let's prove that there are 2 to the n subsets of an n element set. Oh, I was really ragging on this one, but did I assign this as a homework, didn't I? Yeah, okay, all right, I take it back. All right, so. We'll prove that there are 2 to the n subsets of an element set, okay? I think Ryan is who introduced us to subsets and even counting them, and actually literally proved this probably twice in his lectures, but so what? We're gonna prove it by induction. I mean, actually, I'm making fun of the idea of proving things multiple times, but that's like literally my favorite activity in mathematics, is like something that we already know to be true, finding a new clever proof of it is so fun. Okay, so let's prove this by induction. Let's figure out the smallest n for which this makes sense. Again, if n equals what can I get away with here?
0.
Yeah, 0 works, right? Was that you, Evelyn?
Yeah.
Oh, okay. Yeah, good. So why 0 work? A 0 element set is the empty set. How many subsets does it have? 1 itself. 2 to the 0 is 1, right? So it does work, right? So the 0 element set has 1 subset. I'll say 1 equals 2 to the 0 subset. Grammatically, this is very interesting. 2 to the 0 subsets, is that what you would say? Right, grammatically, like 2 to the 0 cars. That's what you would say, right? But that's like 1. 2 to the 0 is 1. You're saying 1 cars?
You're being pedantic.
I never thought of that. That's like cool. Or maybe, I don't know, it's weird. So, okay, subsets. But like it's misleading because there's 1. Anyway, the base case is confirmed. Okay? All right, so let's assume that a what? Tell me the inductive hypothesis. Let's use n minus 1 here. An n minus 1 element set. I'll say sets, right? Every single n minus 1 element sets they're all the same, right? They're just like, doesn't matter what's in them. Have how many subsets?
2 to the n minus 1.
Perfect, yeah. Okay, all right. So now let's consider an n element set. Okay, so let A be an n element set. We name it just so it's easier to refer to here. Maybe it's time for a new pen, huh? You know, we've used many fewer than I anticipated. Yeah.
So you knew Anna was going to crush it.
Yes.
One every 10 minutes.
One every 10 minutes, yeah. Yeah, I should have, this one went too long, actually. Yeah. Okay, so A is an n element set, and, huh? I'm small. Oh, okay, that's okay, Yes.
It's so hard, you guys don't even.
It is actually really hard, yeah. So when we originally conceived of this, there was some idea that a second person would be pressing the buttons for us, and I think that's the way it maybe, I don't know. Next time, like next year. So yes, actually that's perfect. No, that's literally the solution, right? Oh, okay, great. It's like, yeah, expensive piece of plastic. Anyway, all right. So A is an n-element set. I don't know how many subsets it has. I'm trying to prove that. But I do know that sets of size n minus 1 have the correct, not the correct amount, but I know something about those. How do I turn an n-element set into an n minus 1 element set? I mean, I can't really like turn it into, but how do I get one out of it that's useful? And Van's recurrence about these is useful. Any ideas?
Exclude one of the elements.
Yeah, let's exclude one of the elements. Okay, now here is one of the rare instances where we actually cared what the base case was and what the value of n is. When I'm doing this step here, right, what do I know about n? Can n be 0? No, I already handled the 0 case here, so I didn't write it down, but I'm assuming n is greater than 0, it's at least 1. n minus 1 might be 0, but n is at least 1. So I safely can say there is an element in that set A. Okay, so I'll say as, oh, so much better. Oh my God. As n is at least 0, there exists an A in A, some element A in the set A. Okay, I just pick whatever one I want. Okay, consider the set A with A removed, okay? I just took the element, I threw it away. That's some new set. How many elements are in this new set? There were n, I removed 1.
Is n in the set?
No, n is not in the set. That is an A, not an n, yeah.
Oh, I see.
You're squinting too much to be credible as like a, you know, that's an A, yeah. So I removed A, something that's in the set from it. So now I have n minus 1 elements in this thing here. So has n minus 1 elements. So induction says, yeah, wow, maybe we should be changing pens every 10 minutes. This is awesome, yeah. How many subsets are there of this thing?
-1.
Perfect. This has 2 to the n minus 1 subsets. Okay. A little bit of set theory here. Every subset of this thing is also a subset of A, right? It's in A minus little a, so it was in the original A too. But this is not all the subsets of the original set there, obviously, right? Because these are only subsets of what, of a special kind. What kind is that? There's subsets of A, right? Let me write something that maybe helps illuminate this. So A contains A minus A, right? And I've just created a bunch of subsets S inside of this thing here, which consequently live inside of this one here. But each of these do not contain the little a necessarily. But are there subsets of this thing that contain A? Yeah, I mean, A is in there, so there are subsets with it. Those have not been articulated yet, right? I haven't discussed those. However, think about this. Every subset of this thing here that doesn't have A in it, what happens if I do add A to it? It's a subset of this set here that has not yet been discussed, right? This set S here in this thing here doesn't have A. If I add A to it, it's still a subset of this, but it wasn't listed among these ones here. How many additional subsets do I get in that fashion? So yeah, another just exactly this many. For each of these, I can add A to them and get a new subset. For instance, in this list of things, one of the subsets is the empty set, right? When I add A to the empty set, I get the set A, which is one of the subsets here, okay? So adding A to each of these sets, or let's say subsets, gives 2 to the n minus 1 more subsets of A, right? And so at the moment in total, how many subsets do I have? Total number of subsets is 2 to the n minus 1 plus 2 to the n minus 1, which equals 2 to the n. Now, I wouldn't say I'm quite done with the proof here. I think there's one thing worth addressing. I've found 2 to the n subsets of A. I need to make sure there's not more. Maybe there's even more that I haven't described here, right? But can someone tell me why this is all the subsets? Why I've actually taken care of all of them? It goes back to something Van talked about, and then Ryan will talk about after 1 a.m., that all the subsets of A here can be classified into 2 groups. Those that contain little a and those that don't contain little a, right? Every subset of this thing either has little a or doesn't. There's no third way here, all right? The ones that don't contain little a are here. They were this quantity that I established there. Those that do contain little a, if you think for a little while, they are literally just the subsets of these with a added to it. There's no other way to get a subset of a, right? Because you can look at a subset with a, remove a from it, and then it's just one of the ones I described here. There's nothing else, okay? So this is the end, right? That's all of them. Okay, all right. I mean, it's not the worst induction, but yeah, all right.
You did a nice job.
Thank you. Yeah. Okay. Only have an hour left? Oh boy. Okay, all right, so now we're gonna start picking nice ones. Okay, this one's funny. Feast your eyes on this for a moment here, okay? And tell me when you notice something remarkable.
That's not true.
Thank you, Ryan. This is false. This is a typo. I don't know what it's supposed to be. N cubed minus 3 is not divisible by 6 in general. Plug in a few numbers. Plug in 2. 2 cubed is 8, minus 3 is 5. That's not divisible by 6. Okay, maybe it works for a larger number. 5. I don't really want to take, okay, 5 to the third is 125, minus 3, 122. That's sure, no, definitely not divisible by 6. Maybe there are values that are divisible by 6, but maybe we can prove like it literally isn't. I don't want to do this
Does the
one.
induction step work? Is that what these ones?
It's not meant to be this, but no, I couldn't get the induction step to work either. In fact, that was when I was prepping this, I was like, man, I can't figure this one out. Like, it's really this induction. What is the cool trick here I'm missing? And then I was like, oh yeah, it's not true. So we won't do that one. There is another one here. This one's really, I really like this one though. So we can do this. This one also has a non-inductive proof, which I will tell you afterwards as well. Okay, so 2 to the 2n minus 1 is divisible by 3, okay? All right, so, and we even say for all natural numbers, so let's check the base case here. Yeah, it works for the base case, right? So base case is when n equals 1. We're claiming that 2 to the 2 times 1 minus 1 is divisible by 3. What is 2 to the 2 times 1 minus 1? It is 3, yes. Is divisible by 3. A very simple but often handy fact that 3 is divisible by 3, okay? So the base case works here, all right? Now let's assume the statement for n minus 1, okay? So 2 to the 2 n minus 1 is divisible by 3. Okay? And I want to show that 2 to the 2n minus 1 is also divisible by 3. Okay, well, let's just see what happens. Let's write 2 to the 2n. I already don't like it. I think we should have gone from 2n to 2n plus 1. Do you guys see why that's a little bit better? It still works here fine, but like, I'm kind of stuck here. Like, I want to expand this or do something with it, and there's nothing to do, okay? So we're gonna do the other version. You can absolutely do it here. Just the other way is like more straightforward. So instead, we're gonna go here. Say that's divisible by 3, and I want to prove that this one is. Is divisible by 3, okay? Let's write this as 2 to the 2n plus 2 minus 1. Okay, it wouldn't have been that hard to do the other one now that I see the trick, but anyway. Okay. I'd like to see this in this form here, right? How might I do that? Anybody remember their exponent rules? Well, there's a lot of things I could do here. I'm going to turn this into 2 to the 2 times 2 to the 2n minus 1. That okay with everybody? You add exponents? Okay. And let's write this as 4 2 to the 2n minus 1. Okay. Any ideas now what to do?
Subtract 4 and add 3.
All right, nice.
Subtract 3 and add 3, which makes minus 4 plus.
Yes, the fancy 0, right? Yeah, so let's, this 4 you mean, right? So, okay, Daniel, I don't know if this is exactly what you said, but what if I write 4 as 3 plus 1 instead? Is that what you meant? Or did you have something different?
Then I said make the -1 minus 1
Oh.
plus 3. And then you can
Okay, let's do what you said. What I said I think works here too, but yeah, let's try what you said. Okay, so 4, 2, fancy 0, 2n, and then you said turn the minus 1 into
minus 4 plus 3.
minus 4 plus 3.
And then you can factor out of 4. It becomes
Oh, yeah, that's very nice. Yeah, very, very nice, yeah. So replace this -1 with a minus 4 plus 3. And then let's factor out the 4 from both of these. 2 to the n, 2n. Oh, wait. Did we not even need to? No. Okay, minus 1 plus 3. Everybody agree with that step there? Now, this 4 is immaterial, because what do I know about that?
it's divisible by
Yeah, this is divisible by 3 by the inductive hypothesis. And what about this? What did I promise? I said that it's an often helpful fact that 3 is divisible by 3. If this number is divisible by 3 and this number is divisible by 3, the entire thing is divisible by 3. We can prove that, but you can also say, oh, you can factor a 3 out of the whole thing, for instance. Okay? What's that? Oh, come on. At the end of the proof? Yeah. No, it's not on you, Russell. No, it's okay. Or you guys, it's all right. All right, there's the proof. So let me show what I was thinking here since we have some screen now. So instead, because this is cool. Instead, I was going to say with this, I'm going to turn the 4 into a 3 plus 1. Right? So turn this into a 3 plus 1, and then 2 to the n minus 2n minus 1. And then multiply this out, 3 times 2 to the 2n, and then plus 2 to the 2n minus 1. And it works by some other trick. This is divisible by 3, because there's a 3 there, and this is divisible by 3 by induction. That's kind of sweet, right? There's like a few different ways to go about doing it. Okay? This is in induction problems with divisibility. It's almost always stuff like this that works, is coming up with these fancy 1 and fancy 0 type tricks. Okay? Let me tell a non-inductive proof of this. I came up with this while I was trying to prove it by induction, and like Daniel did a few slides ago, where it was like, oh, just do this, and it's like, oh, you didn't even need induction. So it may not be readily apparent, but this expression is a difference of 2 squares, right? Difference of 2 squares are awesome. Right? So why is this a difference of 2 squares? Let me write it in a way that might make it clearer. You guys agree with that assessment? And now it's clearly a difference of 2 squares. This thing squared minus 1, which is a square. What can you do with differences of squares? You can factor them nicely. How does this factor? It's always something minus 1 and something plus 1. And in this case, the something, it's just the thing inside of the square. That it's an exponential itself isn't important. So 2 to the n and 2 to the n. Okay, now, look at these two numbers. What's their parity? They're both odd numbers. Does everybody see that? They're 2 to the n, which is even, plus or minus 1. They're odd numbers. And how close are they to each other? They're 2 apart, right? So we have two odd numbers that are 2 apart. One of them has to be divisible by 3, right? Let's see if we can convince ourselves. Now I'm a little less sure.
5 and 7 aren't.
Oh man, okay. Yeah, so, okay, we probably have to use the power of 2-ness here.
Why would it be 5 and, wouldn't it be 5 and 9 since they're 2 apart?
No, because this plus 2 would be this one here, right? So it's like literally a difference of 2 between the two, right? So 7 and 9 would be good, but 5 and 7 definitely not good. What was I thinking? I probably wasn't thinking. All right, homework. Like, I don't know, see if you can make this work here.
Another one.
Yeah.
It actually uses a proof you already did. 2 to the 2n is 4 to the n.
This,
No, just the first thing.
I see.
That's 4 to the n minus 1.
Oh,
And that divided by 4 minus 1.
divided by 4 minus 1.
You actually proved what this is equal to.
Oh, that's awesome, Ryan.
Yeah.
Everybody see that? That's way cool. Okay, so 2n minus 1 is that. And let me try and divide it by 3. So instead I divided by 4 minus 1. But this is the geometric series formula. This equals 1 plus 4 plus 4 squared plus 4 to the third plus up until 4 to the n minus 1, right? But what type of number is this sum here? It's an integer. It's a sum of fact 2.3 again, right? Sum of a bunch of integers. So if this thing divided by 3 is an integer, the thing is divisible by 3. Yeah, that's awesome. I heard the bell toll 12. That's a daunting thing. There's a lot of, so. I have to be in a classroom in 12 hours, actually, for instance. All right. Yeah, so I'm not the only one. Okay. All right, let's see. Okay, you can't not do this one. This one's extremely cool. I have to explain what's going on, though. All right? So there's a whole setup, but the induction here is so neat. I wonder, yeah, all right. So let's imagine we have a huge chessboard. Okay? And it has dimensions 2 to the n by 2 to the n. They're powers of 2, okay? So it could be 8 by 8, 16 by 16. Let me do an actual example that's 8 by 8, okay? Okay, so 2 to the 3 by 2 to the 3. I hope I got 8 by 8, okay? And one of the tiles here is poked out. I don't know which one, not necessarily a corner, just somewhere. Say this one here is gone, okay? So this board has 8 times 8 minus 1 squares on it, right? And now I'm asking if it can be tiled, we have to explain what tiled means, with L tiles, okay? So L tiles are tiles of the following shape. They just cover 3 squares like that. And a tiling means that I can lay these things down so that every piece is covered, every square is covered, and I'm not allowed to do things like this. I can't have a tile go off the board, and I can't have a tile use this empty square either. That's forbidden, okay? So I just want to cover up the board that way. So you guys understand the question here? All right. Let's see if we can just do it here. We're going to prove that it can be done in general, but it's a good warm-up to see if we can make it work here. I'm going to try randomly and really hope for the best. Yeah, okay, let's just see what happens. It's easily trap yourselves, but let's see if we can not do that. So like one would want to make layers like this, but you have to be careful because this like throws that off there. I see, Daniel, you're trying to work it here. That's good. Okay. So far so good, we're like almost certainly going to fail, right? But you don't think so?
We're too big to fail.
Okay, I kind of don't have, okay, I did have a choice, but I'm really gonna, no, I didn't do it, but I bet it could be repaired, right?
Oops. You can't make a 3 by 2 square at the end.
No, yeah, and that's the whole, I don't want to do that, right? I have to, okay, anyway, I didn't accomplish it, but the whole beauty of this proof is like I don't have to. Daniel, do you see a way to repair it here? No, okay. But you guys see what I'm trying to go for, right? I want to lay these tiles down in such a way that I can. Maybe it would have been better to do a 4 by 4, right, to prove this. That's a little easier.
Pretty sure you and I could do
Yes, yes, yes. But because we're going to prove this by induction, what's the board I actually have to do to start with?
2x2.
The 2x2 board, right? And Russell, what's the 2x2 board look like here?
It's 4 squares with 1 knock.
It's literally an L tile, right? Like this is the 2 to the 1 by 2 to the 1 board. I crossed out that one, but does everybody agree they're all symmetric? I just placed the L tile. Yeah, Ryan, you see the placement here?
See where you
Oh, over here?
No, on the two.
Oh, okay, all right. Yes, good job. Yeah. So that one can be done, doesn't matter where I cross it. So the base case works, right? The theorem is proved in that instance there, okay? Let's figure out how induction can help us, okay? So the inductive hypothesis says that a 2 to the n minus 1 by 2 to the n minus 1 can be L-tiled. Right? It can be covered with L-tiles. Somehow. Like, we didn't do it here, but it can be done. Okay? Now, the fact that this dimensions here are powers of 2 is very important. Let's imagine that I have a board here that has dimensions 2 to the n by 2 to the n. Does it contain 2 to the n minus 1 by 2 to the n minus 1 boards in it? Yes. And how many? Yeah, 4 of them. So let's just split it down the middle here and here. Okay? So there's 2 to the n minus 1 by 2 to the n minus 1, 2 to the n minus 1, and so on and so forth. Okay, so I get 4 boards of that type there. Okay, now I'm missing something. My original 2 to the n by 2 to the n board, what did I not display?
There's a hole.
There's a hole somewhere, right? It's in one of these quadrants. You'll see that it won't matter, but let's suppose it's like, say it was there. That was the missing square there, okay? What does induction allow me to do at one step here?
That entire bottom quarter.
Yes, perfect, Russell. This one can be done. That's missing a square. It's a 2 to the n minus 1 by 2 to the n minus 1. This can be L-tiled. Okay? Can this one be L-tiled? Like literally no, there's no chance because the L-tiles cover 3. Like the parity doesn't work out. There's not enough things here, right? I mean, if it can cover this one and come up 1 short, there's no way it can come up here and not. But that's okay. What if we do this? I'm going to artificially knock out these 3 tiles. I'm going to punch those ones out in advance. Can I L-tile this one? Yeah. Like it didn't matter where, that could be anywhere. It happens to be there because I said so. Tile this. Okay, that's not covered, but the rest can be tiled. The rest can be tiled. The rest can be tiled. I've almost covered the full board.
It's an L tile.
I just literally took out an L tile there, right? Isn't that cool? It could have worked if I pulled off one here, here, and here, but then I wouldn't have been able to place an L tile at the end. So I very cautiously chose those ones there. And they were the 3 quadrants that weren't this guy, right? If this one were here, then I would have taken that L tile instead, right? It's easy to figure out what to do. This is a cool proof as well because it doesn't immediately tell you how to do it. Although if you think for a little bit, it kind of does. How do I do a 4x4? Well, look at the middle part and cut out an L tile and then do them however you do this one. And you can recursively get an algorithm here.
I think Cory.
Yeah, Ryan.
Also in the sense of proof that 2 to the 2n minus 1 is divisible by 3.
I think it is. Yes, I think it actually is. Yeah, that was sort of bouncing around in my head here, but we have now, the number of squares on this board is 2 to the 2n minus 1 after we pop this one out of here. And if it can be tiled with tiles of size 3, then all that many squares have been covered by, they are divisible by 3. So it proves that as a bonus, which is not what it set out to do. Huh. Yeah, that's actually really cool. So like, this thing here is almost like Daniel's idea of the like, turning the 1 to the 4 plus 3. I think that's exactly what's going on in disguise. Oh, that's awesome. Huh. All right. All right. Okay, I'm not going to do this one. It's good, but I didn't prep it enough, and like, I will utterly fail to do my trig identities It's kind of a neat one. Actually, the bigger problem is you do have to do some foiling out, and like it's just too much writing. So
Ryan will come back and do it.
Ryan will come back and do it. Yeah. I mean, I can do this one, but it's okay. Fine. It's so elementary. But I mean, okay. No, sorry. But it's new.
Intro to discrete class.
Yes, I know. Yeah. All right. So the sum of the interior angles of a convex n-gon is pi times n minus 2, right? Here's my n-gon, and let's switch over here. Okay, what's my base case? What's the smallest n-gon there is? Yeah, triangle, 3-gon. Yeah, so n equals 3 is the case here. Okay? What's the sum of the interior angles in a triangle? Yeah, it's 180, which is, it's pi to after all, it's pi, right? So sum of angles is pi. Actually, I got a good question for you. Why is the sum of the interior angles 180 in a triangle? Because they said so? Like, I don't actually remember why. Does anybody know why?
Yeah, this comes from geometry.
Well, yes, indeed. But like, that's like this thing, everyone, you always know it's 180, but like, actually, why?
I think you could probably do some sort of like, you like extend the line, you have complementary angles. Thing.
Some Greek stuff?
Yeah.
Okay.
I mean, it's all Greek.
Sure. Yes, yes. Okay, but this is actually an instance where the base case, like we're just taking this on faith, right? Like, okay, everyone said 180, but like we didn't actually prove it, but well, let's work with that, okay? All right, so then let's suppose that if we have an n minus 1 gon has interior angles, they should be pi times n minus 3. Everybody agree with that? You see the proof? So say this is my n-gon. Can I transform it into n minus 1 gon easily? Yeah, like draw one of these diagonals to chop off a triangle. What's the sum of the interior angles of this one? Right? It's pi times n minus 3. And what am I missing? Yeah, I'm missing the rest of this angle, the rest of this angle, and that angle was never touched. What's the sum of those 3 angles? It's pi by the base case. That's pi times n minus 2, QED. Right? Pretty easy, right? Okay, it's not bad, but it's like so easy. So I could not remember how to prove the sum of the exterior angles. That one's actually cooler, but I don't remember off the top of my head. So, all right. I guess good short ones are fine. Okay, I don't want to do this one, but I do want to do this one. This is a really good example of a problem that has a difficult base case and a easy inductive step, which we haven't really seen except for the last example. Okay, so this is the triangle inequality and the generalized triangle inequality, one of the formats. Okay. So let me switch over to this so you can see the full state. Oh, you know what? Actually, let's do this because I haven't done this yet. Okay, just so we can gaze at it in the Twitch chat in its full glory here. So the one variable version is expressed there. X plus y absolute value is at most the absolute value of x plus the absolute value of y. And if you have n variables, more generally it holds that the absolute value of their sum is at most the sum of the absolute values there. Okay. Yeah. All right. So let's prove everything here. All right. So induction on n, right? When n equals 2, we need to confirm this formula here. You might actually ask, is the formula valid for one variable? If we only have one variable, what is this saying?
X1 is less than or equal to x1.
Yeah, x1 is less than or equal to, our absolute value x1 is less than or equal to absolute value x1. That does actually hold. So that base case could work, but you'll see that we need the version for 2 variables in order to get the inductive step to work, okay? So let's just keep in mind where we end up, why we needed to prove this 2 variable one, okay? Okay, so the base case is when we have two variables, and what we're trying to establish is that x plus y absolute value is at most x absolute plus y absolute. This is tricky, it's not that hard, but let me see if I can remember what to do here. How about I look at some notes? Okay. That's not enough. Okay. I'm writing that. You guys with me? Since I'm squaring, the absolute value doesn't have any effect. That's just multiplying out. I'm going to add absolute value signs here, not here yet. Still haven't done anything, right? Okay. How about that? Now I've finally done something of interest. So this is this, is this, is this. Is this inequality? Everyone okay with that? I put an absolute value sign around xy, which can only make it bigger than before. In the particular, if x times y could be negative, right? And then if I put absolute value signs around it, this thing got bigger than this thing here. If x times y was positive, then there was no change made here, okay? That all right? Now, in fact, let's rather do this. Right, absolute of a product is equal to the product of the absolute. Why do I like this format here? Right? My variable is absolute x, absolute y. If I FOIL them out, I get this thing here. And I'm done. Take the square root of both sides. Right? Cool, right? Not that hard, but like, you know, it's not trivial. Okay, so no, this is so putting these things together implies this. Okay, so just some manipulations with the square established this guy here. So I know we'll hold for 2. Maybe in principle we could try some similar trick where I FOIL out an n term, you know, sum there, but you know I don't want to do that. Ryan's going to teach us the binomial theorem in a little while. So instead I want to prove this thing by induction. So my inductive hypothesis will be what? That this statement here works for n minus 1 variables. Okay, what's the statement for n minus 1 variables? x1 plus x2 plus up to xn is at most, not xn, xn minus 1, up to the n minus first variable, is at most x1 plus x2 plus xn minus 1. That look like the inductive hypothesis, just the one with one less variable. Okay. Okay, now I would like to prove that the absolute value of n variables is at most all of them together. So let's write that out. So x1 plus x2 plus up to xn minus 1 plus xn. I look at that, okay? Now I know that if I looked at just the absolute value of these pieces here, I could break it into this. But I don't have that. I have this extra thing hanging around here. But here's the trick. Let's just pretend this entire block here is some y. So I have two variables. I have this big variable and that little variable. So this here is at most the absolute value of x1 plus up to xn minus 1 plus xn. I have not used the inductive hypothesis yet. Do you guys see what I did here? I used this formula. I used the base case at this point. I've basically never done that till this point, where I use the base case in the, well, I did do it in the previous proof, but very rarely did I use the base case as a tool in my proof, okay?
Makes the last one seem pretty cool.
Yeah, okay, fine. What do I have to do to finish the proof here? apply induction to this, right? That's like just sitting above there says, oh, you can break that up into the component terms. So this is at most x1 plus x2 plus xn minus 1 plus xn, which was this one here. That's it. That's the end of the proof, right? Inductive hypothesis and the base case put together spits that out immediately. Okay? I think it's worth saying that this is harder than this, which is rare. That's the first we've kind of seen of that. All right? There's another very good instance of that, and that's this. You guys have probably seen this in your Calc 1 course even. So you remember the product rule for derivatives? The derivative of f times g is, you do all the mixing stuff, right? It's derivative f times g plus f times derivative g. And you were probably taught that if you have the derivative of fgh, and you take the derivative of that, you get a big mess of derivatives and non-derivatives and whatever. And the trick is like, oh, pretend f and h are one function, and g is its own function, and just like iteratively apply it, okay? And you can do this to find this horrible thing, that f1 times f2 all the way up to fn derivative is like this mess. And it's like maybe not even easy to figure out what's actually expressed there. I'm not going to prove this one, but you do the exact same trick as before. First, you prove that base case, that f times g factorial derivative is that thing there. How do you prove that? That's even harder than the last one. Like I'm asking you, how do you prove the product rule for derivatives?
Calculus?
Some point in calculus, advanced calc usually. I don't think this is typically taught in ordinary calculus. So you'd have to prove that somehow. It's not that bad, but it can be done. It needs limits. And then to do this thing here, you need to use the inductive hypothesis, which will have n minus 1 functions, and you need to use the two function version as well. Put them together somehow. It's almost identical to the previous slide, but that does work out. It's not very nice to write out, to be honest with you. So, okay. We haven't even talked about strong induction. Maybe we're almost there. Oh, I want to do one of these. These are cool. Let's do this one so that we can be sure to at least get one. Okay, let me turn the camera back on. All right. Oh, you can't see it there. All right, so here I have a baby, very, very simple Python program, right? Those of you familiar with coding and with Python, it'll be evident what this is. If you're not, I mean, it's okay. My 11-year-old, who is quite fond of fiddling around with Python, told me that the parentheses around the n equal 1 are not necessary. Is that correct? Yeah, yeah. He was really upset that I put those in there and was like, well, what? Like, I don't know. It's more, anyway, so.
It's in every other coding language.
Yes, right, exactly, right. But I mean, it's awesome that you don't have to, but it's like, if I'm reading a conditional statement, it's really helpful to, I don't know, isolate it, maybe. I mean, it's nice that you don't have to, but you can, I guess. So, all right, so this function, what does it do? It's supposed to return a factorial, right? And you would never write this Python program because there's, the math package, which will just compute factorials for it. This is not fast, right? Python already is notoriously not fast, and you don't want to run a recursive program here to determine a factorial.
It's fast though, as they would have a bunch of wrappers around C.
Sure, right, okay, yeah, fine. So, yeah, anyway, anyway. So let's see if this program actually works. Like, how would we prove an induction for something like this? Well, what is our theorem here? Our theorem is that this piece of code, when given an input, well, n better be a natural number, will actually spit out n factorial, right? I'm not going to deal with possible errors and so on. Like, we're not going to get into too much detail here, okay? But actually, the inductive proof is very easy here in this case, okay? So let's think about this. So my theorem is that this program does what it claims to do, okay? So theorem, I'll say, factorial of n returns the mathematical value of n factorial. Okay, again, on input n is an integer at least 1. Oh yeah, I said on input n at least 1. I should have said integer there, of course. Okay, so how do we prove this by induction? Well, what's the base case? That my theorem holds when n equals 1. Let's analyze this. When n equals 1, what does the program do? It returns 1, right? Just read it out there. If, like, it literally input 1, if n is equal to 1, return 1. Okay, good. So n equals 1, then I'll say factorial of 1 returns 1. How do we know? Because we analyze the code. That's what it does. That's what it does, right? Okay. Is that good? Yeah, 1 factorial is 1. So it does do what it says it claims to do in that case. Great. Okay. What's the inductive hypothesis? Anybody see? What should it be?
Factorial n minus 1 returns n minus 1 factorial.
Yes, exactly. Which sounds like a proof, but like that's, right? Yeah. So the inductive hypothesis says the program does what it claims to do on input n minus 1, right? So factorial n minus 1 returns n minus 1 factorial. That's our inductive hypothesis. We're assuming that it does this. I don't know that it does, but if I can prove that this tells me that factorial n gives me n factorial, then I would have established it. Okay, so let's analyze this. Factorial of n does what? What type of input are we going to be giving to it? I didn't specify and I haven't been, but what type of input are we looking at in this instance here? Yeah, an integer, and in particular one that's at least 2 or greater. If it's 1, we already handled that case, right? So it's at least 2. Okay, so let's look carefully at what this says. The program runs, and the if is not satisfied. N is at least 2, it's not equal to 1, so it doesn't return 1. It runs the else clause, and returns n times whatever factorial of n minus 1 gives us. Okay, so this returns, I actually don't know how to write this. N, should I write a multiplication symbol or should I write the code? Like this, worlds are colliding here, right? It's, I don't know. I'll say n times whatever the output is of factorial. I mean, this doesn't matter. Factorial of n minus 1. What does factorial of n minus 1 return? N minus 1 factorial according to induction, right? So n times n minus 1 factorial, and n times n minus 1 factorial is n factorial. So it does what it says it does, okay? Very simple. This is one of the reasons induction is so valuable to computer scientists. However, computer scientists don't prove their code works as a rule of thumb. No, I mean, no one does. They shouldn't be singled out for it. But it can be, at least recursive programs. The other problem is, most computer scientists, I would say, don't write recursive programs, right? It's we tend to avoid them, although they can do in a pinch. I love them because I'm very comfortable with induction, and so I'm like, oh, I can just do it recursively and like make it work by magic or whatever. But yeah, anyway. But you can prove other programs work through inductive. In fact, iterative ones, I mean, if you have for loops and so on, there's an inductive argument hiding in the background as well. Okay. Let's see here. Amazing, we made it to strong induction, and I'll have, oh, okay, that's fine. I'll have time for a few. Okay, so I do not want to spend a lot of time explaining to you guys what strong induction is for 2 reasons. 1, it's boring to add to it, and number 2, this is amazing, but like, isn't this literally what you guys are doing for tomorrow's class? Later today's class, right? Yeah. So all I'll say is, what's the idea of strong induction? In strong induction, it's actually even hard to express exactly what you want, but in strong induction, you don't just have to go from the previous to the next. You can use any of the previous things to help you get to the next, okay? If for some reason it's convenient that the n minus 5th case helped you prove the nth, you may use it instead. Actually, that was always available to us. We just tend not to introduce induction that way because it seemed to be confusing that way. The latter metaphor isn't as nice.
Dominoes aren't as nice either.
Dominoes aren't as nice either. Yeah, that's exactly. But like, it's okay. So when I assume something like this, hey, assume it returns the correct input on n minus 1, I'm allowed to assume it returns the correct input on n minus 1, on n minus 2, on n minus 3, on n minus 4, everything. I can use any of those I want, and then I need to prove the next one. That's the only difference. You just get more stuff. For all the examples we needed, the more stuff didn't help us at all. But there are instances where more stuff helps us a lot. In fact, we can't do it without the more stuff. All right? And so I have to be, all right, I need a little more to drink, but yeah. I need to make a decision about which one to prove here, or 2. There's one really cool one. I'm definitely I'll definitely finish with a really cool
When
one.
you put it that way, it sounds like you should prove the really cool one.
Yeah, okay. Agreed. You guys convinced me, or I convinced you to convince me. Let's see. Okay. This one is also very cool. But this one will take me the remainder of the time. But at least let me read it to you because it's really funny. So, okay. You don't get chicken nuggets in sizes 6, 9, and 20 in America anymore. I think you still maybe in Australia. Every couple of years I check and see what's up. But like I just want to know, like, as long as the question valid, and you can put whatever numbers you want here. Well, it's not quite that simple, but
This is nugflation.
nugflation's right, sure, yes. So with boxes of 6, 9, and 20, a thing you might ask is like, well, what quantities can I get of chicken nuggets, right? Like, okay, you can get 6, you can't get 7, you can't get 8, you can't get 9. I mean, you can get 9, sorry. No 10, no 11, you can get 12, 2 boxes of 6. 13, no. 14, no. 15, yes, a 6 and a 9. 16, no. I can keep going for a while here, right? And you just have to sit down and check what you can get. And it turns out you can't get 42, I don't think. Otherwise, this would have been written differently. But you can get 43. Anyone see how you can get 43?
You can definitely get 42.
Yeah, you can get 42.
Yeah, okay, maybe I must have.
You can get 42.
7 boxes of 6.
7 boxes of 6. Maybe you can't get 43. Maybe 43 is the biggest you can't get.
You can't use a 20 because there's no combination of 6
Yeah.
It's 23.
And
we know 6 and 9 is going to be divisible by 3. And
Right.
3 is not, so.
yeah, I think you're right, Keith. I think 43 is the highest number you cannot get. 44 and above, you can get all of those. This is misstated here. But it would be interesting, and that's the first interesting thing to find is what's the biggest you can't find. Well, if you know what the biggest is you can't find, you know that you can get the rest. That would prove this here, but anyway. Okay, anyway, so maybe I'll go on. I don't want to prove this one. It's not that bad. The idea is the following. You will assume that you can get everything between, say, 44 and 50. Okay? That's the base case. That's a new base case. You do a bunch of individual things, but that'll be your base case. How do you confirm the base case for 44 up to 50?
You find them.
Just do them by hand, right? Just figure them out. In fact, many of them have multiple ways of doing it. Just show that you can do it, okay? Now suppose I want to get 51, okay? How can I get 51 with the knowledge that I can get 44 through 50? What's 51 minus 6?
45.
45. Can I get 45? Yes, somehow. I mean, I can get 45. I mean, yes, clearly, but I somehow can get it. So if I know how to get 45, how do I get 51? Add a 6-piece, right? Okay, what if I want to get 52? Add a 6-piece to the 46. You keep adding 6 pieces forever. So you need to find this range of 6 values in a row that you can all get. And if you can get those, you can get everything. From that block of 6, you can add 6s to each of them and like shift your range. Shift your range, shift your range. The 9s and 20s only help make the beginning easier, right? I could do shifts by 9 and even shifts by 20, but why make life harder for you, okay? That's the general setup. And those of you that are probably working on the homework, or maybe not, there's a question with stamps, I think, 4-cent and 3-cent stamps. That's this in disguise, right? So I've given you a big hint for how to do that. All right. But let's not do this one. But there was an important thing here, that something new, we had to do more base cases. That was the thing we didn't have before. That comes up in these ones. Okay, all right. No. No. No, because there's a better one. Oh man, no, there's so many good ones. Okay, hold on. Okay, I really like this one, and you guys can help me with this. This is so fun. This is a divisibility type one we've seen, like those others, but it involves not concrete numbers, but Fibonacci's are concrete, but this says that every 5th Fibonacci number is divisible by 5. So 5 divides f of 5n, okay? Let's say for all n greater than or equal to 1, integer, of course, okay? The base case is claiming that 5 divides the 5th Fibonacci. What is the 5th Fibonacci? It is 5. We can 2, 3, 4, 5. Fifth Fibonacci is 5, is divisible by 5, base case confirmed. Okay. The inductive hypothesis is that 5 divides f5n minus 1, right? That's f, the same as saying 5 divides f5n minus 5. Right? Okay. I would like to show that f5 is f5n is a multiple of 5. What tool, there's only one, can I use to work with Fibonacci's?
Induction.
Okay, I'm using induction, yes. What?
Ratio.
Okay, how do you know that?
It's on the homework,
Oh, is it? Oh yeah, it was, okay.
I did it.
Here, check this out. Oh, yeah, okay, all right. We're not gonna use that, that's on the next slide, right?
Use like something cool, like a recurrent.
We could use the recurrence for the Fibonacci's, right? And then you guys will see how this one will work, and I probably won't finish it for you, but you'll see how this goes. I can rewrite this as what? What's the rule about Fibonacci's? The previous two, yeah, exactly, Russell. So f 5n minus 1 plus f 5n minus 2. Does induction say anything about those? No, induction's about 5n minus 5. It doesn't say either of those is divisible by 5. How do I transform these into this? Keep on doing it, exactly. So, okay, f 5n minus 2 times 2. I'm applying it to this one to get another one of these, and then I have an f 5n minus 3. Everybody see that step I did there? I just applied it to this one. I didn't apply it to this one. Are we closer? We're closer, but we're not there.
Are we?
We are, although it's very easy to mess up and not be closer. Okay, let's do it again. So when I expand, this one will be 5n minus 3, 5n minus 4. The 5n minus 3 has a 2 in front of it, and there's another one there. So I'll get a 3, f5n minus 3, and then an f5n minus 4, right?
We get 2 of those, maybe?
Yes, 2 of these. Is that right? Because, wait. No, wait. This became a 3 and a 4, there's a 2 in front. There's a 2. Right? These ones, it's absolutely essential you do not mess these coefficients up. If you do, you will not finish the problem. I've seen it many, many times. Okay.
I think we're close.
We're close, so now we're close. Let's expand this one again. So this one will give us, there'll be a 3, this will be a 5n minus 4, 3 of them with the 2 of these. Oh, beautiful. So then it's going to be a 5, f5n minus 4, right? 3 of them from here and 2 more that were left over here. And then just 3 f5n minus 5s. All right? You guys see it? We're done. All right? This is divisible by 5. Why? Because of the 5. Like, this one probably won't even be divisible by 5 on its own, but there's a 5. And this one is divisible by 5 by induction. QED. Right? Why did we need strong induction here? Actually, yeah, you had to go back 5 steps, right? We didn't use the knowledge of the one previous to this, but 5 previous. You can rephrase this one carefully, though, with an induction on n, because this became, I think. Let's just keep with Russell's answer. We had to go back by 5, not by 1, so we need to use a previous guy here. Notice, though, we didn't need to do 5 base cases, because it always dropped down by 5. Yeah, which is a giveaway that ordinary induction was probably okay, but anyway, okay. So this one is very cool. I'm not going to prove it, but I do want to talk about it a little bit, because I think it's totally amazing that, okay, that's a closed form formula for Fibonacci numbers. So what this means is if I plug in n equals 100, the right-hand side will tell me what the 100th Fibonacci number is, okay? Does that seem plausible to you? No, right? The right answer is no. Why does it not seem plausible to you, Van?
Well, because square root of 5 is an irrational number.
Yeah, like how are you going to get an integer on the right-hand side, right? There's like no way. You have 1 over root 5, a 1 plus root 5 over 2 to the n. Well, you have to, because that's the formula, and Fibonacci numbers are integers. So it actually proves that the right-hand side is an integer. It turns out that the root 5, like they cancel just perfectly. Like it's set up in a way that like everything cancels out. The induction is not that difficult, but it relies on a very important property of the golden ratio. That's a golden ratio inside of there, right? If you square the golden ratio, it's the same as adding 1 to the golden ratio. That's a weird thing. Only a few numbers do that. That's the number that does that. And it's a complementary pair. That's used in the proof, okay? All right. But I don't want to prove that one either. Okay, let's look at this one again. So here, the proof of this would be very similar to the factorial one, right? When n equals 1 or 2, this is going to return 1, and indeed the first two Fibonacci numbers are 1 and 1. For any larger one, you're going to return the sum of the prior two Fibonaccis, and if those were correct, then when you add them together, you get the next Fibonacci. But notice for this, we did need strong induction because we needed not just the previous Fibonacci, but the two previous Fibonacci, right? So this was a good instance where we needed it. But this proof would have gone exactly like the factorial one with a slight wrinkle. Okay. So I really like this one for many reasons. We can prove this one, it's pretty quick, okay? So this is what's called Zeckendorf's theorem, and what this says is that every number can be written as the sum of distinct Fibonacci numbers. If you give me any number, I can add up a certain number of Fibonaccis without repeats to get that number, okay? There's this cool footnote. This is Zeckendorf's theorem. That's what it's known as, but it was proved 20 years prior to him by someone named, I don't like to make fun of people's names, but this guy's name is way cool. Check out that name, Lekker. That's like a real, it's a Dutch name. Actually, Zeckendorf's Dutch as well. Shout out to that guy. I mean, that's so cool. So anyway, but let's prove their cool theorem here. Okay, I'm not going to prove uniqueness. It's lengthy and not, it can be done with induction, it's usually done with contradiction. Let's just see that it can be proved, that we can find this expansion. Before we do that, let's try and actually find a few values. So, tell me.
Is this true the number 2?
What? Say again?
Is this sort of, I mean, like, I guess, the number 2?
2. Yes, okay, so yes, you can repeat 1 because the first and second Fibonacci's are distinct even though their values are the same. So you are allowed access to 1 twice, but no other numbers twice. Right, so like let's write down the numbers we have access to, right?
I'm worried about the uniqueness.
Well, I mean, yes, I see. So you're saying, I see what you're saying. If you could get 4 with a 3 and a 1 or a 3 and a 1, right? For like a different one.
I think you can't use, 1 is a Fibonacci number, so you can use 1, but you can't use.
Oh, yeah, okay, never mind, sorry. 2 is a Fibonacci number, you can use 2 itself. Yeah, you're not allowed to use 2, sorry, you can't, I misspoke, yeah, Anna corrected it. You can use, 1 is a Fibonacci, you can use 1, you can't use 1 twice. Yeah, so 1, 2, 3, 5, 8, 13, 21, what do we got here? 34, isn't like 55? Why would 55 be a likely candidate for the next one? Yes, previous problem, right? Anna, you are, yes, the camera's off, thanks. Yeah. Yes, okay. So we have these and so on, right? More Fibonacci's. Okay. Let's just find a few of these Fibonacci representations real quick. So, okay, how do I write like 19 with Fibonacci's? Okay, there's one representation. Turns out it's unique, like I said there, although I'm not going to prove that.
What about
5?
5? Well, 13 plus 5 plus 1.
Yeah, what's going on here?
5 plus 8 plus 3 plus 2 plus 1, 2.
Yes, of course. What am I doing wrong here?
So 3 plus 2 is 5, which is the Fibonacci number, right?
Yes.
Does it have to be like the largest Fibonacci numbers made from their like pairs?
I think you can't do consecutive Fibonacci numbers.
Okay,
I think
yes. Then, do you have a statement of the theorem up by any chance? I must have written down something wrong.
Zeckendorf's theorem states that every positive integer can be represented uniquely as the sum of one or more distinct Fibonacci numbers in such a way that the sum does not include any two consecutive Fibonacci.
Okay, cool. Everybody catch that? Yeah, so that's exactly what Daniel said. I'm not allowed to do this. Okay, so append the theorem. You're not allowed to use two consecutive ones. Very good. Yeah, that's great. Okay.
13, 5, 1.
So then, yeah, then we'd have to use the 5 here. We'd have no choice. Yeah, without that, we've also just discovered that it wouldn't be unique, clearly, because you can, if you happen to have that, then you can make a substitution every time. Okay, interesting. All right, so that's one. There's others, right? Okay, so let me see. I haven't proved this in like 10 years, but let's see what happens. Okay, well, we know the theorem. So base case. N equals 1. Can that be represented with Fibonacci's? Yes, it is a Fibonacci. Okay. Now we actually see the format of a strong induction proof here. So let's let n be greater than 1 and assume all k less than n have a Zeckendorf representation, let's call it. Okay? What do I mean by that? I mean exactly this Fibonacci representation where there's no two consecutive in the representation. So I claim all the numbers below n can be done in some fashion. It's the same idea in the chicken nugget theorem that we could do those 6 in a row. That would be part of an inductive hypothesis. Okay? So everything that's smaller than the one we're working with can be done. Okay, and now I'd like to find a representation for n. Okay? I know all the smaller numbers have them. Suppose algorithmically you were trying to find this representation. If I wanted to write this as a unique, or with Fibonacci's, what would you try to pick at first? Try to find, yeah, exactly. Find the biggest one that doesn't go over n and start with that, like assume that's going to be in your representation, okay? So let's fix n, say, and find largest f sub j such that f sub j is at most n. So this is the biggest Fibonacci I can get such that fj plus 1 is now above n there, okay? If we're lucky, what might happen here?
It's f sub j.
F sub, yeah, n might literally be f sub j. It might be a Fibonacci. That's a possibility. So if f sub j equals n, then we're done. Because what's the representation? It's f sub j. Just write it down. You don't have to do anything. Okay. Otherwise, this means that n is strictly larger than f sub j. So I need to figure out the representation for n minus f of j, right? Whatever the representation for this here will give me the representation for n. Just solve, right? This will be equal to like f, L plus f t, and I don't know, whatever they are. I don't want to give them subscript names because there might be a lot of them, okay? But there's some representation. I mean, is there? Yeah, induction says so. That's a number that is smaller than n, and every number smaller than n has some Fibonacci or Zeckendorf representation.
We have to make sure that it doesn't include f sub j minus 1.
So yes, yes. So that's absolutely correct. So we need to make multiple checks here. There is one, but it might not be valid if, say, fj appeared, because then I'd be reusing fj, or even if fj minus 1 appeared, that would be problematic. So I do have to check that. So what we'll do is suppose that happens and see, okay? This part's actually really sweet, okay? So does everybody see? Done, otherwise, what am I writing here? And we're done, otherwise, okay, this is greater than 0, let's say. So it has a z representation, okay? I don't know what that z representation is, but let's look at the biggest Fibonacci in it, okay? Ryan pointed out that there's a problem if the biggest Fibonacci in this representation is another fj or an fj plus 1, right? Minus 1, yeah. Let's assume that happens, okay? So if it includes an fj, then this means that the representation for this number here has an fj in it and maybe some other Fibonacci's. So what it means in particular is that n minus f sub j is greater than or equal to f sub j, and potentially other terms. Maybe it's equal to that there. So this means that n is greater than or equal to f of j plus f of j. What is that bigger than? F of j plus f of j is bigger than what Fibonacci? Yeah, the next one, right? In fact, let me even write this. It's clearly larger than f of j plus 1 minus 1, which is equal to f of j plus 1. Can n be bigger than f sub j plus 1? No, because I said f of j was the biggest one that was below n. F of j plus 1 is definitely above it. So this is out. What about the other situation? That's also resolved at the same time. Everybody see that? What if instead I had, it includes f of j minus 1, the previous, then I just skip this step here. Then this is bigger than j minus 1. Then this step is erased. N is greater than or equal to f of j plus 1, f of j. I mean, yeah, you get that. So it couldn't have been either. Isn't that sweet? That actually fits together very, very nicely to make that work, okay? This is a good instance of proof over theorem. Like this proof gave us the fact that you won't have two consecutive ones, even though the statement didn't have it, okay? All right, so, all right, I got to do the cool one. I promised you guys. So, oh, that's not it. Where is it? Oh, it's after this. Okay, not that one. That one. Okay, and this one has a fatal flaw too. Like there's not x's and a's, there's one or the other. So I'm going to rewrite the statement on the board, and we're going to prove this one. And this is a really cool journey here. I may need some notes assistance here, but, and I'm extremely hungry. So give me a moment.
It was so tough when Jack came in with his dinner. Oh my God, just so
Yeah, that is tough. Yeah, actually, by the way, you guys, I mean, maybe a lot of you guys are going to take off immediately, but what do you think about getting some like pie hole delivered? You guys like pizza?
Yeah.
Okay. I mean everyone, not just the speakers. I'm going to have a couple pizzas delivered, so, you know, you don't have to stay up or anything, but I don't know. All right, anyway, okay, we'll talk about it in a moment. Yeah.
pie hole.
Yeah, I mean, it's nice too, but it's like the only joint that actually you can get food from, you know, at this time. I think they deliver, right? They must deliver. I haven't ordered from them in a while, but.
If not, I can go running rapidly.
Sweet thing, all right. All right. Okay, let me erase and then we'll prove this one. Were you actually gonna go there, Daniel? Okay.
If I was like, if I was not gonna eat food, I was gonna leave before 2 and go get that. I haven't eaten anything today and don't have food at home.
Oh man, there is snacks at least to hold you over till then.
I've had some stuff.
Okay.
I haven't had a meal today, which does my whole pizza count as a meal?
Sure.
In this economy, yes.
All right. I want to prove the arithmetic geometric mean inequality. I'm just going to rewrite it since what's written there is a little bit problematic. So actually what I'm going to do to reformat this, so those AIs should be XIs, first of all. All this says is if you take the geometric mean of a bunch of variables, what does that mean? It's no pun intended. X1 times X2 all the way up to Xn, take the nth root of them. That'll give you like the multiplicative average of those values there. That is at most the ordinary arithmetic mean on the right-hand side. Sum them up and divide by n. Again, those AIs are XIs, it's just a typo. Okay, that's what this mean inequality says is the geometric mean is at most the arithmetic mean there for real numbers. Okay, what I will do instead is I will take the nth power of both sides just so the statement's a little cleaner. So that'll say that x1 times x2 up to xn is at most the arithmetic mean to the nth power. Everybody agree that's the same statement, just take the nth power of both sides. So I'll write that down, we're gonna prove that instead. So x1 times x2, xn is at most the sum of the xi's over n to the n. Okay, that's what we're gonna prove by induction. All right. So we will need a base case here. And this one's fun because we're going to use the base case as well, like some of the others. So what's the base case here?
N equals 1?
Okay, yes, and does n equals 1 work? So if you just have x1 here, then you have x1 over 1 to the 1. It does actually hold.
Cory, you're small.
Yes, I'm small, thank you. Am I? Oh, okay. Yes. Yeah, right. Thank you for the compliment. I feel famished, so, you know, it's anyway. It's like, what does Bilbo say? He feels like too little jam spread over too much toast or something, you know what? Too little butter over, okay, yeah, butter, yes, good. That's how I feel right now, but, all right. So Van's right, the base case for one variable does actually work, but we're going to need, like we did in the triangle inequality, the case for two variables in order to get this to go forward. So we gotta prove that one way or another. So that statement would simply be x1 times x2 is at most x1 plus x2 over 2 squared. Now, this is the base case. I don't know if this is true. I need to actually prove this, okay? Now, you may have seen the arithmetic geometric mean inequality often is this, literally. You may have seen this before, but we need to prove this, okay? So I'll say want to show this. So we'll do that first. Okay, so how do we do this? The trick is very similar arithmetic trick to what we did in the triangle inequality. I will write down a clearly true statement and FOIL it out and end up with this at the end, okay? So the proof of the base case is the following. Take x1 minus x2 squared. I claim that that is at least 0. Do you guys agree with me? Who cares whether x1 or x2 is bigger? Squaring a number gives you something greater than or equal to 0, okay? This implies, well, just FOIL it out, x1 squared minus 2x1 x2 plus x2 squared is at least 0. Okay, getting closer. I'm going to now add, I'm going to move this over to this side here, and then add an additional 2x1, okay, better to say, yeah, I don't want to say it that way. I'm going to add 4x1, x2 to both sides. 4 times x1, x2 to both sides, okay? So that'll give me x1 squared plus 2x1, x2 plus x2 squared is greater than or equal to 2x1, 4, x1, x2. Okay, and now I think I'm there, right? This is x1 plus x2 squared greater than or equal to 4x1, x2. Divide both sides by 4 and bring the 2 inside, so I'll just do that quickly. Right, and that's that. Okay, so it gave me that. This follows from this thing here, okay? That's cool. So I'm gonna erase this because we're gonna need the space, but we now know this guy's true. And I'm even gonna give this a name. This is going to be P2, okay? That's, the statement of the proposition for two variables. This is familiar to, many of you, okay. All right, so now, I'm not going to use an ordinary inductive argument here. I'm going to tell you the format, how this is going to go, and then you'll believe me that it proves it for all n. But it's not, the ladder metaphor no longer works. It's now like a, I don't know, you guys can help me come up with the metaphor here in a moment, okay? So there'll be two parts to this proof. Part A will be that the statement for n variables will imply the statement for n minus 1 variables, okay? At the moment, that seems to be worthless. We know the statement's true for 2. This will only prove the statement for 1 from 2. This is the wrong direction, right? I don't want to climb down the ladder, okay? What's that? Yeah, we didn't do, yeah, right. We didn't do 1, so we get 1 for free, but like this will not be helpful, right, on its own. Now B, this is where the cool stuff happens. In B, I will use the truth of Pn and P2, right? P2 I know, I've proved, and Pn is going to be the one I assume. These two together will imply P2n, okay? This together with the base case P2 will prove my thing. Look how this works. We can still look at the ladder. All right, okay. So if I know n, then I can get n minus 1. If I know n and 2, I can get P2n. When I start this whole process, what do I know? I know P2 only. What if I put n equals 2? I know P2, and P2 implies what? P4. So our ladder's actually, we're going to say it starts at 2. Knowing P2 can get me up to P4. Now, what do I know? I know P4 now. That'll give me P3. So drop down to P3. Now, I know P3 and P2, so I get P6. Okay? But knowing P6 means I know P5. Now I have P5 and P2. Okay, now it gets a little more interesting. Now I go up to, wait, do I have to, no, I'm good. Then I go up to P10. That's probably not P10, but let's just pretend. Now it's a little different. I know P10, so I can get what? 9, and then 8, 7, and then jump back up. So you see that this gets me everywhere on the ladder, but it's just in this ridiculous way. I'm some sort of acrobat that I can like jump up and then climb down and then jump up and then climb back down. But this is a model for induction, right? It'd have to be some other thing. But like, how does this prove that it works? Well, I just showed you, right? You can, tell me a number, how do you get there? Well, do this until you get there. So what I need to convince you though is this true and is this true for all n? Okay? And this is a work of genius, the way this works. It's completely awesome. Okay, so we've gotten P2. I'll need a little assistance to make this work. Most of getting this proof to work is figuring out what these individual statements are from this thing here, okay? All right, so first we're gonna prove A, okay? A is that if I know Pn, I can get the previous one from it, okay? By the way, if you have P4, you can get 3 and then P2 again, but we already knew P2, so you never go back down the ladder to P2. There's no reason to do that, although you can. Okay, so here I'm gonna put A. A is no longer that A. This is a variable that I'm giving a name, just it's associated with case A. A is equal to the sum from k equals 1 up to n minus 1, A xk over n minus 1, okay? The natural question here is like, why? And the only answer is because it works. You can unpack it a little bit at the end, but all I've done, I haven't really done anything. This is just shorthand for this. What is this? This is the sum of the first n minus 1 variables here, each divided by n minus 1. I can pull that n minus 1 out front if I want, but that's what I call A.
What's the arithmetic mean?
That is actually, that's literally, yeah, you're right, Van. That's worth seeing. This is literally the arithmetic mean of the first n minus 1. They're formatted in this form. I think it helps in the proof to be in this format, but this is actually the mean. So it would be this thing inside of here with n minus 1 and n minus 1 in disguise, just written that way. Okay, then I'm going to write the following. I'm going to have to use this notation, so I'm going to tell you guys what it means here. Yeah, something new, right? Oh, it's a pi. Oh, perfect. Okay. You remember how the sum tells you to add up all the numbers in a list here? This is just the product. This is the product of A1, A2. There's no A's. Despite what the board says, there's no A's. This is the product x1, x2, x3, x4, all the way up to xn minus 1. I'll put it this time. Later on, it'll be inconvenient to rewrite it. But this product here is just x1, x2, up to xn minus 1. That's what that's shorthand for. Just like the sigma is sum, the giant P is for product. Okay? All right. This product times A, okay? A is that thing there, all right? Why didn't I write that out? This thing is a 2-variable product. It is of this form here. X1 is this month. Is that what I want? I think that's what I want. That's definitely what I want. Look how crazy this is. This is this X1, that is that X2, right? This is a number or some product. Yeah, it has a bunch of Xi's in it, but this is just a product of 2 things. P2 says that this should be at most. I'll ask you guys to tell me. What should it be at most? The product, this product? Wait a minute, something's, yeah, I don't like it. I don't like it. I mean, that's not wrong, but that's not, I'm doing the wrong thing here. Oh, no, we're fine. How many terms are in that product? think of A as a product term. There's n minus 1 terms here, and one more term here. There's n terms here, okay? Remember what we're trying to do in A. I'm assuming the n variable version works and trying to establish the n minus 1 variable version works. It doesn't quite look like it, but this is n minus 1 variables and one more, super variable. So I can use this formula here for it. So what is this formula? This says, oh, well, add up all these guys, because these are the these first n minus 1 variables, and that variable there is the big A by itself. So this becomes sum, k equals 1 up to n minus 1, ak, plus A, over n to the n. You guys see that? It's subtle, it's easy to miss it here, but that's what, maybe it would have been better to call this ax, so that you kind of think of it as one of those variables, but I guess they chose A because of arithmetic mean and so on. Okay, all right, so what? Well, check this out. What is this sum? It's right here, right? If I multiply both sides by n minus 1, I get n minus 1 times A equals the sum of the first n minus 1 xk's. So this is n minus 1 times A plus another A, all over n to the n. But what's this? N minus 1 times A plus A over n? This is A to the n, right? Okay, what does that mean? That means that this product here is at most A to the n minus 1, right? Divide both sides by n minus 1, right? So let's write it out here. This is k equals 1 to the n minus 1. xk is at most, divide both sides by A, I have A to the n minus 1, right? A to the n is an upper bound on this product here, divide both sides by A. What's A to the n minus 1? It's this. That's A. K equals 1 up to n minus 1. X k over n minus 1, all to the n minus 1. What have I established with this line here? This is Pn minus 1, right? So I just confirmed A here, right? Maybe it's easier to, this, I could pull this n minus 1 down below the whole thing. It was in every term, right? And then it clearly looks like n minus 1 variables producted are at most those n minus 1 variables added, divided by n minus 1, all raised to n minus 1. That's this statement for n minus 1. So I confirmed this. All right, now I have to erase that part, and we have to get this part here, that using these two together gets me this. And it's a similar trick. I think this one's even maybe easier. I do not have many minutes left with my voice. I can tell. Okay, so for B, let's start working with B directly. So I want to establish this thing here. So I want to prove that the product of 2n xi's, so x1 up to 2x2n, is at most the corresponding thing here with a 2n there, a 2n there, a 2n there. So let's just look at what the left-hand side would be. So proof of B. So product xi, I equals 1 up to 2n, right? Let's break this into the product I equals 1 up to n of xi times the product I equals n plus 1 up to 2n xi. Okay, this is the product of all 2n variables. I took the first n and the remaining n. Just put them together there. Just split them up into two groups. Now, anyone see what to do with this? I've assumed Pn and P2. This is a valid P2. This is one big variable, and this is one big variable. Is that what I want? I feel like that's, no, that's not what I want. No, I'm gonna use Pn here, not P2. I wonder if you can do P2 and then Pn instead, but I'm gonna use Pn on both of these individually. Okay, this has n variables. It's precisely in this form here, right? So this one, by Pn, is at most the sum of the xi's, I equals 1 up to n, over n to the n. Call me out if any of these look fishy. I think I got that one there. This one's the same, just with a different range on the sum. This is I equals n plus 1 up to 2n xi over n to the n. That was 2 applications of Pn, right? Pn was used here and here, just on a different named set of variables. Okay, now what I want to do here is put everything to the n here. Okay, this was to the n, this was to the n, it's just, I'll pull the n outside so I can focus on these 2 things individually. With these, I want to use P2 here. Oh, yes, now I do it. I do P2 on that times that, right? That sum is my x1 and that sum is my x2. So then P2, and we're very close to the end here, is this thing plus this thing. But they're both sums, so I can it's just one big sum, right? x1 plus x2, all of this plus all of this. I transform back into sum mode. Right?
Like a prop.
Yes, over n. And this n up here was all that was done internally to that n there. Oh, and that's what I wanted, right? The product of the 2 n variables is there should be a 2 here, and a 2 here.
You're applying P2, so you get copies of
Oh, yeah, good, Anna, yeah. There's this 2 here from P2, and there's this 2 here, so this is 2 to the n, and then this is, yes. Okay, I don't want to write another thing on the board. I can't take it anymore. But, but this product, this is the right, okay, I have to write it. It's too pretty not to write it. So the sum of the xi's, I equals 1 up to 2n, all divided by 2 times n, 2n, raised to the 2n. That is P2n. So I got it using Pn twice and P2. It all fits together. And then I convinced you guys with the latter that having all this in hand, together with having done P2, says that this holds for all n, okay? Truly a remarkable induction proof. Maybe pushes your boundaries of belief about is this actually induction? Because it's pretty different from those other formats, but it does work, okay? Okay, good. Yeah, that's gonna do it for induction. That was the last induction slide anyway, so we had to skip a fair amount, but let me turn off the camera there. And Ryan will start up in a few minutes. We'll take a little breather here, so.